Hi, good morning. So I'd like to thank Mario for the kind invitation. So this is actually two works in one presentation. One is pretty much finishing. Actually, it's just the beginning, but it's a full first paper. And in between, I'll just mention something that really struck me as a really strange coincidence, but perhaps you have heard it before. So please let me know if it's not news for you, because it is for me. So this is done in collaboration with Karim from Egypt and Richa from India. So perhaps they are watching us. Uh, let's just start with a brief summary with FFR theories. And I'll go from Jordan to the Einstein frame, and the definitions will be clear in a moment. So please hang up tight. And then I will just add some extra fields in the Jordan frame, something like a matter field, a scalar field, just to remind us that there's not only gravity in the universe, there should be something else, us at least, right? And so I'll just go backwards from the Einstein to the Jordan, which is not usual in this kind of FFR theories. And then I'll talk about this conformal-like coupling in the Jordan frame, and how can we make it work if we are using FFR to explain inflation and the preheating in the Einstein frame. So preheating, in a nutshell, is just one of the mechanisms that reheats the universe right after inflation, because it gets really cold due to the exponential expansion. So we will have to reheat the universe in order to have a radiation-dominated universe, really hot and dense, and the standard configuration of GR that we all love, right? So without further ado, let me just make a really brief summary of GR, just to introduce the notation. So we have Lagrangian of gravity. So this is the Lagrangian for the gravity sector only, and this is the action for the matter field, whatever it is, right? So usually the Einstein-Hilbert Lagrangian, that's what we stick with, which is just the Ricci scalar, and we may add a cosmological constant just to explain the current acceleration, for instance, right? So if we do the standard approach, just calculate the function derivative with respect to the metric, then we get the equation of motion, which is Einstein's equation, right? So that's just pretty much standard, right? So what we do in FFR theories is just that we replace our gravitational Lagrangian for a nonlinear function of the Ricci scalar itself. Of course, it should be nonlinear, because if it is linear, then we get back to Ricci plus a constant, right? So it should be something nonlinear, and everything that's pretty much obvious has already been discarded out for many reasons. Background evolution of the universe, solar system tests, or relativistic stars. So many different modifications. The easiest ones have already been discarded for some reason or another, or for multiple reasons. So, but anyway, just keep with me for a second. So if you just follow the same procedure, then you arrive at a much more complicated equation of motion, where f prime is just the FDR, and you notice here that you have fourth order differential equation on the metric. So it has the same degrees of freedom of GR plus something else, right? And in order to materialize that, to make these degrees of freedom more explicit, then what is usually done is this. So we start with the Lagrangian, right? Sorry, there should be a square root of minus g here, right? So I just write this Lagrangian as phi r minus w, where w is phi r again minus f. So it looks like where phi is just f prime, right? Just a shortcut for that. So it looks like I'm just adding and subtracting phi r, because at the end of the day, I still have plus f, right? So I have everything that I started with. But it's not actually just adding and subtracting the same thing. That's actually a Legendre transformation, because I'm changing the basic variable from the Ricci scalar to phi f prime. So this is a Legendre transformation. And then what is usually done is that, okay, so that's now my Lagrangian, right? And then I notice that there is this factor in front of the Ricci scalar itself. And I notice that this is in Wald's book, for instance, Appendix D. If I make a conformal transformation on the metric for any function, capital omega here, then I have to, of course, transform the determinant of the metric itself, obviously. And then I can write a new Ricci scalar, which is calculated from this new metric here. That's what the tilde means, right? Which is just capital omega to minus 2 times the previous Ricci scalar plus some extra terms over here, right? So the thing is that, so if I want to absorb that, if I want to get rid of this coefficient here, which is this one plus the omega that comes from the square root of minus g, then I can make a conformal transformation, and then I'll get rid of that, plus a full divergency, plus something that which is the derivative of the log of this conformal factor over here, right? So at the end of the day, if you pick the correct conformal factor here, you just get rid of this phi over here, because then you have, instead of having the a global factor times the Ricci scalar, then you have only the Ricci scalar. So you're back to Einstein-Hilbert's Lagrangian, right? So the correct conformal factor that you have to pick up is exactly f prime. If you do that, then you get rid of that, and then you can write, I'm gonna just write in the next transparency, the Lagrangian in this new frame. So this is called the Jordan frame, where you define your f of r, where the energy momentum tensor of your matter field is conserved by itself. But now in the second frame, you have only the Ricci scalar on this new metric, plus a kinetic term that comes from omega squared, which is actually a new field. So during coffee break, during coffee break, you can see the poster by João, which is over there. Raise your hand, right? So everybody can look for you in coffee break, because now we're studying some different approaches, consequences of this conformal transformation, right? So just like this is not a coordinate transformation, but it is a conformal transformation. It's not a coordinate transformation, but just as in a coordinate transformation, if you make an ill-defined one, you can have a singularity at some point, just like in Schwarzschild coordinates, right? You start with in Schwarzschild coordinate, there is a singularity in the horizon, in the black hole horizon, but that's only a coordinate transformation. So if you make a coordinate transformation which is singular at this singularity, then you get rid of it, right? So what João is going to show you, no spoilers, is that something similar may happen with respect to a conformal transformation, right? And if you want to know what, then just watch his poster, right? So let's get back to here. So if we make this conformal transformation with the right conformal factor, then at the end of the day, you have only the Ricci scalar in this new metric, right? The tilde r plus a kinetic term, right? Plus anything else that plus you have this term over here, right? Of course, right? So at the end of the day, what you have is this one. You have the Ricci scalar, and you have the kinetic term for this phi tilde, which is just the log of phi, which is f prime, right? And this factor over here is here just to have the right coefficient in front of this kinetic term. And you have so you have this scalar field phi tilde subject to a potential which is given by this, right? So E here stands for Einstein frame, right? So you have the Ricci scalar, so you have all the degrees of freedom of GR, right? Plus the degrees of freedom of a scalar field. So this is just the same description that we had before in the Jordan frame, but you have materialized it, you have explicitly written the extra degrees of freedom in this scalar field, right? So what's usually done is that, okay, so we start with your given f of r because you hit your head in the morning shower, so you wake up with a given f of r that hasn't been tested yet, and then you make the test to see if it's reasonable, if it's stable, and blah blah blah, and then you it can go to the Einstein frame because this is GR plus a scalar field, and you are used to think about GR with a scalar field, and then you see if things work out. But then at the end of the day, you get back to the Jordan frame because that's where the energy momentum tensor of your matter fields is conserved, right? So there is a whole issue about which frame is the physical one. So there is a huge discussion about it. We can talk about it for as long as you want after the seminar, but I don't have much time to discuss that here. But I would just assume that since the T mu is conserved in the Jordan frame, you see there is no tilde here, and it is not conserved in the Einstein frame. So I'm just assuming that the Jordan frame is the physical one, right? So here it's a really nice to make calculations because it's easier. You can use your code, which has already been validated. So, but at the end of the day, you have to go back to the Jordan frame, right? So what I'm going to propose here, of course. So let's assume that sorry, spoiler. So of course, we have extra fields in GR other than the gravity sector, right, in the Jordan frame. So let's assume that we have a psi field, right, which is just a scalar one, just to represent matter, whatever you want, which is not gravity. And then you have to if you want to write it in the Einstein frame, then you have to change the determinant of the metric, right? Square root of minus g over here. Then you can absorb this conformal factor into the definitions of the psi field and of the potential itself, right? So here I'm just assuming that this potential is just a simple one, a massive psi squared. But if you do that, then you have, in order to absorb this phi into this psi tilde here, then what you have to do, you have to define a new field, right, psi tilde, and you have to define a new mass, but that's okay. But you also have to define a new derivative here because you have to put this phi, the conformal factor, inside the derivative, so you can define the derivative of the psi tilde here. And then it turns out that this derivative is this thing over here. Right. So the thing that struck me is it looks like a coincidence, but it's probably more than just a coincidence, because you probably have seen it before in the Higgs mechanism. So this is something that I've been talking to with Mauricio and João, which is his graduate student. So you probably have seen that in the Higgs mechanism, or perhaps in your electromagnetism class, that you can define, there is a gauge transformation, that is a degree of freedom that you have. It's not physical, right? It's just a gauge, right? So you can define a phase for your field, a complex field. So there is a phase because you have this U1 symmetry, right? But then you have to introduce if you want to introduce the coupling to electromagnetism, and then this is the potential vector over here, right? And E is the charge, then you have to define a new covariant derivative here in your field, your electromagnetism, your potential vector must transform like this, and the kinetic term in the Lagrangian for the electromagnetism is this one, right? The antisymmetric gradient of this potential vector, right? So that's the Higgs mechanism, or electromagnetism, or whatever you want to call it. But the thing that we have here in the conformal transformation is that, okay, so our metric, which is the basic object here, is going through a conformal transformation. So it's omega squared. But well, it is, yes. Yes, perhaps I'm just. I don't see why you think it is local. It is because Higgs also relies on that. But I agree, it's a better. That depends. That's right. That depends on the potential and the break of symmetry. You're right. So I should have written here local gauge invariance. Yes. So I'll fix that. Thank you. Yes. So in the conformal transformation that we are going through here, you can write this capital omega, the conformal function, as this thing over here. So that's in terms of the tilde phi field, right? And so this is the conformal, the new conformal derivative that I have defined in the previous page, right? So here, what would be corresponding to this vector potential, it's actually only a gradient, right? That's all that we have here. So A, it's just a gradient. So it looks like this A is just a pure gauge here. And if it is a pure gauge, then there is, it's still working? So there is no kinetic term here, right? Because it's just, if A is just a pure gradient, right? So it looks, for me, more than a coincidence. So it's something that we are beginning to explore. So let's say it's a work in progress, but just because it just occurred to me just a few weeks ago. So I didn't have time yet to develop, fully develop yet. So we are talking about it. So there is a lot to be done here. So let's get back to what we have been doing. What I have in the back of my head is that, okay, so I would like to use this f of r to describe inflation. You know that you can do that in either frame, either Einstein or Jordan, because it's been proven that you can define these low-row parameters if you have inflation in one frame. So exponential expansion of the universe in one frame, you have also exponential expansion in the other frame. So you can work it out in either frame you want, and at the end of the day, you go back to Jordan frame to make this the physical one, like as I said. But the problem is that, so can we use that to describe preheating? And preheating, as I said, in a nutshell, is just that you have a given interacting term in the Lagrangian of your two fields. I'm just going to put tilde here because I'm assuming that happens in the Einstein frame, right? So you have your scalar field that comes from matter, right? And you have your inflaton field, but that actually it's a gravitational sector, right? Because it came from an f of r in the Jordan frame. So let's assume that we have such an interacting term, such as this one, in the Einstein frame. As I said, I'm starting my reading at the Einstein frame. Instead of hitting my head until I think of a really smart f of r, a smart enough f of r, I'm just starting in the Einstein frame with maybe usually interactive term, right? So what we have is that we have the equation of motion for this inflaton field, right, in the Einstein frame. We have the friction term due to the expansion of the universe, and we have the derivative of the potential to what the phi field is subject, which is whatever, right? Because we're starting in the Einstein frame. So we also have the equation of motion for the k modes for this tilde psi field. So we have you have the friction term as before, but you also have this mass term over here. So if it happens that the potential here to which the psi field is subject is if it happens that the v also includes the interaction terms over here, so the tilde phi will, let's say, will be at the bottom of the potential, right, of its own potential. So it's going to be oscillating at the bottom of its potential because that's after inflation, right? So we have this low roll phase, and at the end, its roll is just oscillating at the bottom of its potential. So it's going to be like an oscillating mass for the psi field. So this oscillating mass for a given field, that's the main ingredient for what's called the parametric resonance. It's just like you are, remember when you were a kid and you were at the playground and you were swinging yourself in a swing, and then you had to pull up your legs and stretch them in the right frequency so that you would just increase your amplitude. So you didn't know it by then, but that was parametric resonance, right? Because you are changing your moment of inertia with the right frequency so that your amplitude would increase, right? So what happens is that depending on the wave number and depending on the frequency of your mass, then your amplitude will increase, right? So it doesn't matter if you are changing your moment of inertia in the swing, but you are doing that in the wrong frequency, then you won't enjoy yourself. So you have to match those things, and you do that automatically. But so that's not for any frequency. That's my point. So what we can do is just to figure it out if we just plot this. So this is a plot of the wave number, this factor over here, as a function of G. G is the coupling term that is inside this potential over here, the coupling constant between the two fields, right? So depending on the values of both parameters, then you are inside of one of those instability bands. So the darker shade here, the larger the exponent of your amplitude. So your amplitude increases exponentially if you are inside one of those instability bands, right? And the darker the shade it is, the larger the exponent is as well. So lambda, it's actually I should have this was taken from this paper over here that introduced the subject. And in this paper, the phi field is self-interactive. So you have a lambda phi-4. So lambda is the self-interacting term for the phi field itself, and G is the coupling constant. Actually, it's this D over here, right? So that's made just because of the units. You have to plot that. So those are the two interesting quantities that define where you can use to plot the instability bands. Sorry, I was a little bit sloppy about that. Sorry. So the thing is that we do have something really similar here. This is classical. Yes, it is. As I said, it's just a swing in a playground happens at exactly the same thing. The only thing that you can, well, you can be quantum when you introduce when you introduce the wave numbers here. Then you can talk about the annihilation and creation operators, and you can expand in plane waves and all that. No. Let me be clear about that. That's a good question, actually. Inflation is only made up by this phi field. So that's the inflaton field, only one field inflation. And the psi field is just a secondary field, which is in its vacuum state just before preheating starts. Oh, any matter field or radiation field or whatever, it's going to absorb the energy from the inflaton field when it's oscillating at the bottom of its potential. And then it will, as you can see here, only a few modes will be amplified, right? So if you neglect the expansion of the universe just because this happens really fast, so only a few modes will be amplified. But then with the expansion of the universe, a given mode will just cross this band, right? Because K is going to, the wavelength is going to be stretched by the expansion of the universe. So we have a really turbulent outcome, and then we have to go numerical to find the final temperature of that. So Satish, yes. That's not, sorry? Well, it was, so let me just repeat your question because it's being webcasted. So we are asking if this psi field was created by the previous one. It's not well created, it's not the right term for that. The thing is that you transfer the energy from the inflaton field to your matter field, but it was already there in its vacuum state. So it won't spoil inflation and whatever. Yeah, but the inflaton field is rolling down its potential, and everything else is being diluted away, right? So even if there was some energy in the secondary field over here, then it will be diluted away, washed away due to the exponential expansion of the universe during inflation. So I'm just neglecting, for instance, back reaction from the psi field in this equation here, because it won't matter during inflation, and it will only play a role at the end of the inflation when the phi field is at this oscillating around its minimum value. The phi field? No, it's just coming downhill, right? So it will oscillate at the bottom of its potential naturally, right? Let's just pick a potential. I'll just talk about some 3 examples in a minute. So let me know if it doesn't answer a question then. Okay. So is this thing clear? Okay. So have only a few modes will be amplified. But then if you go numerical, there are packages available that you can use to calculate the final temperature of the universe, for instance. Okay. So what we have here is that in the Einstein frame, we do have a scalar field, right, which is related to f prime, right, which is related to f of r that you picked in the Jordan frame. Right, I haven't said anything about which one it is, right? Because that, so the question is, so in the Einstein frame, let's assume that you have some interaction term, right, such as this one to generate parametric resonance. So what does it correspond to in the Jordan frame, right? If I make this conformal transformation backwards, right? So the simplest thing that I can think of is like a non-minimal, of course, it's going to be a non-minimal coupling for psi, right? So the simplest non-minimal coupling that I can think of is just a conformal coupling, right? So what I'm trying to find out is actually I can write it down because I know exactly what is the relation, the backwards relation, right, between the tilde phi field, the potential, and the f of r, but just in parametric form, right? I should have put in the reference here. It's a work by Magnano from more than a few years ago. So this is no, this is not my work. So if I do that, my question is, if I have something like this in the Einstein frame, so can I have something like this in the Jordan frame? So I can just plug it here, right? The definition of the expression for the Ricci scalar in terms of the tilde phi field, right? And the transformation in the psi field as well. And then I can look for solutions, which is there a V? This is a differential equation for V of phi, right? So is there a V that solves this equation over here? And turns out that there is, right? Surprisingly enough, there is an exact solution for that. The caveat is that it's a bad one. It doesn't work for me because this expression over here C is just a constant and is the power that I had in the previous transparency. So if n is 1, then I do have a minimum around which the potential could oscillate, which is nice to have a minimum, right? But if n is even, so it doesn't have a minimum, right? So that's a bad case. So why don't we stick to n equals 1? Because there is no slow roll phase here, right? So this may work for parametric resonance, but that won't produce any inflation before that. So I don't want an exact solution that doesn't work for me, right? So actually, there's no need for exact solution because if I want the parametric resonance to happen, all I need is a minimum, right? As a stable vacuum around which the tilde phi field will oscillate, right? And if I want inflation, all I want is a slow roll phase, right, before that. But they don't have to be at the same time. Actually, they cannot be at the same time. So since the parametric resonance only happens after inflation, I can think of a few interesting cases. So I can think about massive phi squared. I can think of phi to the 4th, right? And I can think something a little bit more exotic, like an exponential. And that comes from I was inspired by the expression that between the Ricci scalar and the phi field itself. So if there is an exponential over here, then they cancel out, and I have a nice expression for the Ricci scalar in the Jordan frame. I'll show that in a moment. And the 3 parameters here, there was a constant. Oh, wrong button. There was a constant here. So I can, and there's a constant here as well, but it turns out that this constant I can fix, I can choose those constants so that I'll have a precise feature that I'll show in 2 pages, right? So I'll just justify this weird constants here in a moment. So n is just a power, a free parameter, but the factor n to the n or alpha should be the same here, and n should be the same here, just because actually two pieces of information that I'm just requiring. First of all, I'm requiring that, so these are the three potentials, right? The blue one is the squared, phi squared. So the dashed, the dotted black is the phi to the fourth, and the dashed red is the exponential one, right? I'll talk about these dots in a moment. But yes, in the Einstein frame, yes, yes, that's whenever there's a tilde, that's the Einstein frame, right? Yes, yes. It's not exactly the same expression, but the functional form is exactly the same. There is a plateau over here, and there is a minimum around which the field oscillates. Yes, but there's a crucial difference. I'll tell you about in a second. Sorry. No, that's not it. Yes. So those parameters were fixed for two reasons. One of them is that all of them, the vacuum is at 0, and there is no effective cosmological constant either, right? So V of 0 is 0, and the phi is 0 at the minimum, at 0, right? So this is one ingredient, and for the second ingredient, remember that I can. Oh, should be. Sorry, spoiler. So perhaps it's in 2 pages from now, but this. So let me just go ahead to see if it's there. Yes, sorry, they're out of order. But you can see that I do have, remember that I flashed a few pages ago the relation between f and tilde phi. So I can plot f as a function of r because I know both of them as a function of the tilde phi, right? So this is f of r for the quadratic case, f of r for the quartic case, and f of r for the exponential case, right? So those parameters were defined, those three parameters were defined so that I had the FDR equal 1 at 0. So the FDR is proportional to the Newton's constant. So if I want to recover GR at the end of the day, so the FDR should be 0 when the field oscillates around here, right, at the end of the day. So you can see this is a multivalued function, right? But I'm assuming that the phi field starts with a really large and positive value. So it starts around, so let's get the quadratic case. It starts over here, so that low rho conditions will hold. And then the phi field is going to, remember that phi field only sees a quadratic potential, right? So it's going to slowly roll towards the minimum of the potential, and then it will oscillate around the bottom, right? So it starts over here, and then it comes here, and then oscillates around this point over here, and then eventually stops, right? Classically speaking, of course. And then this dot over here, those correspond to the dots in the previous page, and that's a threshold value, because in this branch over here, you can see that the second derivative of f is negative, and that's a known constraint for instabilities in our f of r theories. So as long as the phi field doesn't cross these values, so you don't probe these unstable regions, right? So for those of you who weren't here in the Brazilian school a few months ago, I presented a paper that talks about the thermodynamic interpretation in this case over here. So the different thing there is that the phi field started with a large negative value. So we probe this branch over here. There's inflation in this branch over here. There is instability, but a brief one over here. And then the field crosses, and at the end of the day is oscillating at the bottom of the potential along this curve over here, right? So the difference between, you can see that f of r in this branch here, right, this almost linear branch is different in either one. The only thing that they have in common is that the FDR is 1, right? But you can see that this is not as Starobinsky, because Starobinsky f of r is r plus r squared, and this is not r plus r squared, right? So this is different. So the functional form is different. It looks like the same in the Einstein frame, but not in the Jordan frame. So it's not quite the same. So, so let me see if I change it. So let me come back here. So even for the exponential case, we start over here. I don't remember the exact value that we have to start. So the slow roll conditions will hold for the right number of e-folds. But then this field slowly rolls down the hill and then oscillates around the bottom of the potential. And you can show that it doesn't cross this threshold over here, right? So the same thing happens for the black dot and for the blue dot. So they are never crossed in the corresponding case, right? So you're safe. So, but let's go back to our work. So this is the equation of motion that we have for the psi k, for the k mode of the psi field, right? So we have the same terms that we would have in the absence of this interaction, right? So, but in either case, the quadratic, the quartic, or the exponential one, we have some extra terms here. So all you have to do is just calculate the instability bands in this equation with using this equation, right? So we are assuming the same thing, that the universe doesn't expand because this is a really short period of time. So I'm just going to neglect h, which is a dot over a, and so these terms vanish, right? So all we have is the same thing that we had before, right? These terms over here, and we have, of course, the interaction with the phi tilde term, right? But we know the equation of motion for the phi tilde, right? Neglecting the back reaction from the psi field. So what we have is finally these nice pictures. So for the quadratic, for the quartic, and for the exponential one. So here we have the Floquet exponents that tell us how large is the exponential expansion inside these instability bands, right? So let me just point out that the scale here, vertical scale here, is different for the quartic case. So in the factor here is the smallest one, right? There is a 3 factor between the maximum value here and the maximum value here. So the quartic case is not good enough as the quadratic and as the exponential one. The quadratic is the one that with the highest exponent. So what we had, so this is what I just told you. What we have the oscillation of the phi field in the Einstein frame, but in the Jordan frame, we have oscillation of the Ricci scalar. So if you remember, there is a conformal-like coupling between the Ricci scalar and the psi field in the Jordan frame. So the Ricci scalar is oscillating at the bottom of its potential, but there's no potential for the Ricci scalar. So, but it is oscillating around 0. So it happens that depending on the value of the mass of the psi field in the Jordan frame, where it's actually defined, when you add or subtract the Ricci scalar, besides it not only oscillates, but the effective mass could also be negative, depending on the value of the bare mass of the psi field. So you do have the parametric resonance, although you don't have any potential whatsoever in the Jordan frame, but you have an oscillating mass. And this effective mass might even be negative, which would give then an extra boost to the amplification of the psi field in the Jordan frame, right? So the next step, they're looking forward just to pick up some constraints from this picture, but then you probably have to go nonlinear to use the full numerical evolution to calculate the temperatures and to calculate some perhaps signatures of these mechanisms, such as primordial black holes or some signatures in the cosmic microwave background, for instance. So there's something that you are actually looking into. And I think that's the final one. Okay, so thank you. Fast. I spoke too fast. Yeah. Questions? Yes. Está desligando? I have to keep pressing the button at the bottom. No, press a little bit and turns on. Huh?
Now it's okay.
Yes.
So I am a bit concerned about this multi-branch Lagrangian that you get. Usually this is a serious problem because means that the initial data is not well defined. You lose uniticity. If you want, imagine you want to study geodesics motion, things like that. No, sorry, not geodesic motion. But if you want to study the field evolution, then you lose basically the unique somehow possibility to having a well-defined unique evolution all the way through numerical simulation, because you have a branch, eventually you have to tell what branch you have to choose. That's something
in this
people
case,
are, yes.
It's not working? It is. Right. So in this case, we started with a large positive phi field, tilde phi field, sorry.
But in the Einstein frame.
In the Einstein frame. And
But,
then we have shown that we do not probe the other branches. So we always in this almost linear branch here.
That's okay, but then suppose you are back in the Jordan frame, and I ask you, what is the Lagrangian?
It is okay.
Then this f of r is problematic, no?
Well,
because of this branch.
Not so much, because if you are assuming that you are, for instance, in the primordial universe, right? Then you're assuming that you have a large rich scalar. Then you see that these two branches over here, they end up here. But as I said, you started with a really large R, so you are here. And then there is no other branch over here.
Okay,
so that's the only
but how do you recover the classical limit from your Lagrangian?
By continuity. The only evolution that the field.
No,
the
but in terms of suppose I have this f of r, and then I ask you, okay, you have that. I want to look at low, let's say, energy limit. Okay, so let's say discuss the classical test of gravity, no? Recover the Poisson equation, then you have a problem already, that because you don't know which branch at low R you have to choose, not as at high R.
Okay, but for instance, if you have like a cosine potential, then there is one range of the argument of the cosine, which is the physical one, right? That doesn't prevent you from using a cosine to define your potential, right? So you just have to know that that range is the physical one. So due to just continuity in the evolution, you're not going to probe the other branches.
Okay, then the low energy.
So the low energy.
Suppose you want to discuss recover.
This one.
Okay, the classical physics. Okay, Poisson equation. Okay. Is the same branch, you have the same branch that you will choose for in the case of high energy?
Yes, it's this one. The dashed, I forgot to say, but the dashed line here is GR, when f of r is r. So you can see that the linear, almost linear branch is that where we started is similar to GR at low energy, right? Here, here, or here. So if you do not probe the unstable branch, and we show that we do not, then you have this here. And actually, there is one extra piece of information. So you can write the solution of this equation over here, right? For the exponential potential, there is a particular solution. You can write this, I forgot the name of the function, is the product log function, but it's a multivalued function, actually, but you can fix the branch that you're using. And then you can, the branch in mathematical notation is the branch -1. So that doesn't mean much, but it's a fixed branch that gives this curve over here. And there is another branch that fixes the other branches. It describes the other branch. So if you just hit your head in the shower in the morning and just think about, oh, let's think about a product log function, but in the -1 branch. Where is that? In the -1 branch. So that we wouldn't be asking questions about which branch is the physical, because I started with the -1 branch, and that's my f of r. That's the product log with a fixed branch.
Yeah, but R is what the other branch, no?
No, for this branch over here, it ends up somewhere, right? So just like this one ends and this one ends. So the first one doesn't actually. It keeps going.
But it doesn't end yet. If I can give a suggestion
Please. Yes.
for the right interpretation of your plots, you have to think about a plot in a Riemann surface. So you are folding your thing, so you see this singular point. But if you fold in the other way, this is perfectly continuous. There is no singularity at all. You are going in another sheet of a Riemann surface, which is perfectly all right. And can I suggest to you to have a look to a recent paper of me and Mario concerning k-essence models. We step into similar things. I mean, there are critical points. And the right interpretation, what was going on, is to think that in the second branch, time goes backward. So if you insist in putting only one direction of time, you get plots similar to yours. But if you just open your mind and think that time can run backward in the second sheet, everything goes through perfectly.
Yeah,
so now you are folding, but suppose this line you put in the other side. You see, every point you get no singularity in the derivatives there. You see what I mean?
Yeah, no, the derivatives are not singular. I agree.
Not only not singular, but they have the same value.
Yes. The first derivative, for instance, is always positive here. Yes, but the thing is that. But the thing is that there is a time, the time direction here, preferred time direction, because the evolution of the field here is the Einstein frame. I'm not sure how can I renounce to the evolution in the phi field. Okay, so let me just give an extra piece of information is that when you follow the evolution of the phi field in the Einstein frame, it's just oscillating towards it's just going downhill towards the bottom of its potential. So what happens if you start in a negative value is that you start over here, and then you go here and there. So there is no singularity in the evolution of the phi field in the Einstein frame.
In our case, is the time.
Yes, probably there must be some other variable here that you can flip. It's actually what changes sign is the time evolution of the Ricci scalar. R dot has a negative value in this branch over here. True. Yeah. But you see, if the time in the Einstein frame goes in one direction, the conformal transformation is positive definite. So the time goes in the same direction that the Jordan frame as well. Well, Jordan frame, I happen to be very fond of the time in the Jordan frame, so I wouldn't like it to go backwards.
I mean, if you believe in what you're doing, you have to follow what you find till the end.
Yes, I agree.
That's what Einstein did not do when he found the expansion of the universe.
Mm-hmm.
True. To it because
Yes.
it was out of his mind.
Yes.
Guardare le cose abbastanza uguali.
Non devi andare a uscire. Devi vedere l'equazione del modo, quella cosa lì. Non le puoi manco scrivere, perché le derivate
sono superfici di vita.
ma l'equazione del modo non le puoi scrivere perché le derivate sono scritte.
Non è vero.
Ma non devi andare a uscire. Tu devi proprio scrivere l'equazione del modo.
Parlando per questo.
Ma dai, mi sta chiaro.
You cannot define the derivative at that value of far. You cannot just write the equation of motion. That's it.
No, the derivative here is well defined.
It's the on-shell, the solution. Maybe you have a solution with the equation of motion.
You have time to discuss this later in the coffee break. Okay. Another question. Okay, we'll have coffee break until 10:30, and that's it.
Thank you.
Thanks.
cima, não.
Ah, ok.
Esse daqui, o pointer é aqui.
Tá, tá. Pode ver aqui.
Esse é o fora.
Okay. So thank you, Mario, for the invitation, for the talk. Well, I will talk about the wave function of the universe, more specifically, what should be the meaning of the wave function of the universe, or in other words, what kind of information, of physical information, we could extract from the wave function of the universe. This is a very important question for quantum cosmology. So even if you have a perfect theory for quantum gravity, everybody is concerned about this theory of quantum gravity. If we don't address this question and apply it to cosmology, we will know what is the physical meaning of the question of this quantum theory. So this is very important for quantum cosmology. I think it's half of the question of what should be quantum cosmology. Okay. And this is not a trivial question. This is a very important question, and I'll try to show you why this is so important. So, as everybody knows, the cosmology has initial singularity, the standard model of cosmology, which is based in the Friedman models. All Friedman models contain a singularity, and it's a point where no physics is possible. So, a nice way to attack this problem is to think, well, the characteristic size of the universe in the far past of these Friedman models was much, much smaller than an atomic nucleus. So perhaps quantum effects should be important. And also, the universe is a physical system. Why? Because there is a theory behind it, of cosmology, behind cosmology. They had predictions made with this theory, like the expansion of the universe, the cosmic background radiation with anisotropies, abundance of light elements, and many others, which were confirmed by observations. So you can think that the universe is a physical system. Now, if quantum theory is fundamental, it should be applied to all physical systems. Hence, why shouldn't we apply it to cosmology and help with the problem of singularity? So that's the question. Now, the problem is if you stay in the usual Copenhagen interpretation, there is a big problem. Why? Because, as you know, because of the problem of quantum measurement, well, as Van Neumann tried to understand it by constructing a wave function for the physical system, for the apparatus and everything that's around, and postulate an interaction which mimics measurement. He showed that the wave function bifurcates in all the possible eigenvalues of the operator that are being measured. But in the end, only one branch is observed. You don't see all these possibilities, just see one. So what Copenhagen interpretation says about this? It says that, well, actual facts take place in the classical world, and the apparatus should be classical. And the classical apparatus interacts with the physical quantum system and realize a collapse of the wave function and turn the quantum potentialities into actual and unique facts. Okay. So there has been some developments. For instance, de Courriers can explain why you do not see macroscopic superpositions. For instance, the famous Schrödinger cat, when the wave function bifurcates and the possibility of the cat dead and the cat alive, de Courriers shows that these two branches do not interfere. But it does not explain the unicity effect. The coherence is not sufficient. It's important, but not sufficient. And so that's why we need a collapse postulate and say that somehow, somewhere, the branch which we do not observe collapse. So if you want to do quantum cosmology with this, you cannot. And Rosenfeld was very clear with that. Don't come to me to talk about cosmology. Cosmology is something classical, has nothing to do with quantum mechanics. Don't come to me to talk about cosmology or quantum cosmology. So in the covariant interpretation, quantum cosmology even doesn't make sense. No sense at all. Should not think about it. And here we see some realization of something that Einstein said about quantum theory. He said, contemporary quantum theory constitutes an optimal formulation of certain connections, but offers no useful point of departure for future developments. And this is one, okay? So if you stay in a covariant interpretation, you cannot talk about quantum cosmology and forget about it. But now, if you have alternative quantum theories or alternative interpretations, like the many worlds was really constructed for quantum cosmology. Okay? It's constructed because of that. Consistent history approach, spontaneous collapse, where the Schrödinger equation becomes nonlinear. There is a nonlinear term in the Schrödinger equation, trying to physically implying a collapse, and the de Broglie-Bohm theory. I will talk more about these two possibilities because there are some comparison between them already made in quantum cosmology. And well, I don't have time to talk about the others, but there are also many things about the others. Okay, let me first try to explain in 2 slides what is just to have an idea of what is it. The consistent histories approach was developed first by Griffiths, then Omnis, and then Hartree and Gell-Mann. So what are histories? Histories are a succession of properties. An example of a property is that the eigenvalue of an observable B is in the domain D in time t. A property can be described by a projection operator in the subspace of eigenvectors corresponding to the eigenvalues of this domain, on this domain. So what should be the probability of a property? So the property is given by a projector operator, okay? What should be a probability? A probability should satisfy this requisite here, and because of some Gleason theorem, it's a node theorem, you can say that this probability can be given by the trace of some traceless positive operator rho. You can understand as a density operator, a trace of rho times p. Okay? So what is the proposal? The proposal is that the probabilities are now assigned to history. So you have an history. It's for instance the probability of that operator some values at t1, the probability to have the other operator some value at time t key, and so on. Okay, this is a history, and this should be the probability. Proposed to be the probability. So if rho is just a pure state, this is the probability is just this, a projection of psi and pi 1, which is the usual thing that we know. Now, if you have now a family of histories, take a family of histories, then you have to compare the probabilities. What's more probable, this history or this other or another history? Now, if these histories do not intersect, then this must be satisfied. The probability of a history and another history which do not intersect, then should be the sum of the probabilities. And this is an important requirement, which is difficult to be satisfied. Huh? Yes, but this kind of probability, the probability of history is not really in the Copenhagen interpretation. They use all the machinery of the Copenhagen interpretation, but but they developed this notion, as you see, much further, which no one did before. So the first one was Griffiths, then Omnis, and then Gell-Mann and Hartree trying to apply to cosmology. Okay, but in other, they try to keep us as close as possible to. They develop this notion in the framework of projector operators and others. Now I have to satisfy this, and this is not easy. And then what they do, they construct a decoherence functional, which is this thing here, which gives this is a history and this is another history. And the sufficient condition for this to happen, that you can sum the probability, is that that this thing is zero, but it's not the necessary condition. The necessary condition is much more complicated, and so many people stay with this sufficient condition. And if it is satisfying, then the probability is, you can calculate, and there is no problem. However, let me tell you something now. Where pays the probability of the history age. So the idea is to use this and give the probability of different possible histories for the universe. Okay? The problem with that is that still is missing something, which Omni say in the last chapter of his book. Because you have this many possible histories, but in the end, we see only one history. So how in this mechanism you can obtain only one history? How you can obtain the unicity of facts? This is an open question also for this. Okay? And Omnis was very clear with this. He developed everything. You can construct a logic, and it's very nice, a very intricate construction. But in the end, he says exactly this. But let us continue. And let us talk about the other alternative. Now I will skip this because I don't have time, I think, to talk a lot about this. So let me talk about the de Broglie-Bohm quantum theory. And in the de Broglie-Bohm quantum theory, it's assumed, in the non-relativistic picture, it's assumed that the position of the particles have a reality. And so you must give an equation for this. Okay, this was first proposed by de Broglie, and then Bohm developed it. In the case of fields, the fields are the amplitude of the fields. They have objective reality, and you also have to give some equation, some dynamics for the fields. And this dynamics is valid everywhere, in the macroscopic scale and also in the microscopic scale, no, the microscopic scale and on the macroscopic scale. Okay. And so for the wave function, so a physical system then for him is to specify a quantum system. You need the wave function or the state, but you also need to know the position, because this characterizes a quantum physical system. So for the wave function, we have this equation here, which is the Schrödinger equation in the case of non-relativist particle physics, but you can also construct a functional equation in the case of fields. And this equation here gives the velocity of the position of the particles. And this S here is the phase of the wave function when you saw here. Okay, this is called the guidance equation. So the particle the particle is guided by the phase of the wave function in this way. Okay. Now, if you write down this equation right in this form, writing the psi in this form, then you have this a complex equation. You have two real equations. This one is the usual continuity equation. And this other one is like a Hamilton-Jacobi equation supplemented by this thing here. It depends on the norm of the wave function, and which is an extra thing in this kind of Hamilton-Jacobi equation. So note here that if you assume this and without this term here, this is just classical mechanics in the Hamilton-Jacobi formulation. But if this thing is not is important, then the trajectories are not the classical trajectories. But there are trajectories, but they are not the classical trajectories. So that's why Bohm called this the quantum potential. Now, this equation here the solution of this equation here depends on some initial position. You must give some initial position. But you don't know the initial position. If you want to try to measure the initial position, if it's a very small quantum system, you interfere with the quantum system and you lose information of what we had before. So the only thing you can say is to say about some distribution of initial positions. So In this theory, the initial position is the so-called hidden variable. Now, if this distribution of initial positions at some initial time is exactly the norm of psi square, then using these equations here, we can show that at a different time, at any other time, the probability of finding the particle at some time is exactly norm of psi square in this time. So all the statistical predictions of quantum mechanics are recovered. So it is, if you say this theory is equivalent to, in terms of probabilities, to quantum mechanics. However, Valentini, who will be here tomorrow, he'll talk to us tomorrow, he thought another thing. Well, suppose that the distribution of initial conditions is not psi square, but some function with the continuous function, well defined, and all these things. So he showed in a cross-grained level that this distribution, because of these dynamics here, rapidly relaxed to norm of psi square. So the so-called quantum age theorem of Valentini. So it's more or less, they use the same techniques as to show that the entropy of a statistical system goes to its maximum. So that's why he called this quantum equilibrium. But this is not a theorem. You can find some situations where this is not at all true. But in general, for everything that you know here in the laboratory, as everything interacts with many other things, you can show that this it's almost always true. But one thing that's interesting is to find some system where this is not yet reached, and then if you find a system where this is not yet reached, then you can find possibility of observable difference between this theory and the usual Copernican theory. Okay? But that's the thing that these people try to find out. Okay. Now, how this approach? Capital P. What's
capital P equals what is capital P? Is it of probability?
Capital P is a distribution of probability. Just some.
What is the equation of capital?
No, the capital P he should satisfy more or less the same equation, because you see, because if you think if you have an initial distribution, okay, and these are the velocities. So here you see, this is the velocity. So if you have an initial distribution of particles, we have real, have objective reality. This is something like a fluid. So the capital T will evolve with the same equation. We evolve with the same equation. Think of in terms of a fluid. We evolve with the same equation. Okay, that's why they coincide. That's why it is used in order to find this theorem between quotes. It's not really a theorem. The indication that this happens almost to everything that exists now. Okay. Okay. Now about the measurement problem. So these are the problems, as I said. Now, and the problem is really because it's completely similar. This branch and this branch, there's nothing to distinguish one from the other. So we have to postulate a collapse. But in the case of this quantum approach, so say that you're talking about the Schrödinger cat. So the Schrödinger cat and everything that's surrounding the Schrödinger cat, the Schrödinger cat is described by a point in a very big configuration space, which has objective reality. Now, this point will evolve through the dynamics, and depending on the initial values of these positions, it will go either here or either here. So if it goes here, because this thing has objective reality, it distinguishes this branch with respect to the other. And you can show that this other branch, which is the empty branch, does not affect any observable thing, any instrument, and you cannot detect this other branch here. So you don't need a collapse. You can say that this thing continues to exist, but is undetectable. And the particle here breaks the symmetry because it goes in this way, for instance, and then distinguish the two branches. This is very powerful. So you don't need a collapse postulate in this theory. This is a picture of the trajectories in the interference experiment. When I first saw it, I was very shocked because in all my courses of quantum mechanics, very good teachers, the book of Feynman, they say, well, the interference pattern shows that you cannot even think about trajectories. You cannot even think about trajectories. And when I saw this, I go, wow, but this was wrong. There is a possibility to think about trajectories, and they are calculated and they are here. So we should throw a bunch of electrons, and depending on the initial positions, they have one has this trajectory, the other has another trajectory, and all this thing. And in the end, you see an interference pattern. Okay. No, this is we have a interference two-slit experiment. Have a two-slit experiment. So you throw one electron. You can throw an electron one by one, or you can throw a bunch of electrons. So depending on the initial position, if they come here, they come here, and this is the initial wave function. It's a Gaussian. Usually you treat as Gaussian. So for instance, you take this electron here, you take this trajectory here, or this one. You take this trajectory here, or this one. So there are many electrons, all of them, each one has a trajectory. And in the end, you have this interference pattern. Okay? So no, but even in quantum mechanics, usual quantum mechanics, if you throw one electron, and this is already done, if you throw one electron, what you see is just a point in the screen, just a point in the screen. Okay, just a point in the screen. This is already done, just a point in the screen. So you see the interference pattern only when you throw a lot of electrons. Okay.
I think you close one of the doors.
Then, yes, yeah. Now then, you have the trajectory you give in the end the same pattern that we expect in usual quantum mechanics. Yeah, but this is no, because you see the initial wave function. There is one initial wave function, a Gaussian in the first slit and a Gaussian in the second slit. And then you let it evolve, then you have a big wave function, then you calculate the trajectories. But if you close the other one, then the function comes only from this Gaussian. And then the final wave function at any time will be different. And then the trajectory will be different. And they accommodate with the final result. And it's because if you assume the probability of initial conditions is normal psi square, when you talk about probability, it will give the same thing as quantum mechanics, even in the relativistic, also in the relativistic framework. Okay.
But this is a classical probability.
If you say that. No, if you assume that, let me try to. If you assume that initially the distribution of initial positions is normal psi square, then it's always normal psi square. But
So
you must have.
wave function.
Yeah, it's a complex.
It's enough.
Yes. Yeah.
So it's a classical probability.
Yeah, if you say that is, yes. But what Valentini tried to show, and is valid in almost all situations, that even if you assume that's not true and some t equals 0, it goes to normal psi squared because of all these dynamics here. Okay. Which is very nice. So I was really shocked when I saw this for the first time, and not only me, but Bell. What he says is, I think, is very important. In 1952, I saw the impossible done. It was in the papers by David Bohm. The subjectivity of the orthodox version, the necessary reference to the observer could be eliminated. But why then had Bohr not told me of this pilot wave, if only to point out what was wrong with it? Why did von Neumann not consider it? Why is the pilot wave picture ignored in textbooks? Should it not be taught? Not as the only way. Nobody's advocating this is the only way, but as an antidote to the prevailing complacency, to show us that vagueness, subjectivity, and indeterminism are not forced on us by experimental facts, but by deliberate theoretical choice. I think this is completely true what he says here. Completely true. And I think everybody here must have this in mind. Okay? Yes, especially this last thing here. All these things are not forced on us by experimental facts, which sometimes I learned that it was forced by experimental facts, but it was wrong. Okay, let's move on. Let's now apply everything to cosmology to try to give a sense. And then I will show that in cosmology, we can have discrepancies between one approach and the other approach. Okay? Let us just think about a homogeneous isotropic geometry and a scalar field. We can touch both, but it's a very simple thing. So this alpha key is log of A is the scale factor. So the Hamiltonian is very simple. It's just a homogeneous anisotropic geometry and field. And so it's just the momentum P alpha square and P phi square. Okay. And the classical solutions are this is alpha, this is phi. You can think of phi as a specific time. It's something that comes from a singularity and expands forever, or something that comes from very infinite volume and goes to a singularity. These are the two solutions, always with singularities. Okay. Now, the Wheeler-DeWitt equation is just an equation that this is a constraint. If you use the Dirichlet quantization procedure, the constraint must annihilate the wave function. If you do that, this is the equation that you have. And in order to construct a measure, you take the square root of this equation in this way. You can do this. This is a scalar field without any potential. Okay? And choose an psi single field approach. Then you can define a physical scalar product. This is the thing that was done in this paper here. Okay. Now, in this paper here, they use the consistency approach in order to find out what is the probability to have a bounce when you do this quantization. And this is the probability to have a bounce. The probability that at minus in time phi as a time minus infinite alpha is bigger than some fiducial value alpha star, and phi plus infinite alpha is also bigger than some fiducial value alpha star. So if you have a bounce, it must satisfy this, because a bounce is something that should go from alpha infinite, never go to minus infinite, and then goes to plus infinite. And they found that the probability for this bounce is 0. Okay, so they say, oh, the Wheeler-DeWitt equation doesn't solve the singularity problem. Okay. With respect to this approach, that's okay. However, in the de Broglie-Bohm approach, if you write down the general solution for the effective Klein-Gordon equation that you have, this is a specific case, and you choose this UK here and VK here as this Gaussian, and you calculate the trajectories, then you can see that, well, you have something that goes from the singularity, expands to, and goes back to singularity, but also you can have something that comes from a classical contraction, then experiences a bounce, and then goes again to classical expansion. This is alpha, and this is phi. And this is alpha equals 0, or perhaps the Planck length. And so you see that here, above here, there is always a bounce. But below here, there is a singularity. Now, this was a particular solution, but in this is a particular solution that you have already obtained in 2000, the years 2000. So people should have known about this. But we developed all these things in order to give a result in general for any kind of possible solution. And for any kind of possible solution, using the Broglie-Bohm approach, we have proved that the probability of having a singularity goes from 1/2 to 1. So you have possibilities to have situations where there is a bounce. And this is the particular solution where this probability is just 1/2. Okay. So these are conclusions that have a conflict here. And this is the first thing I want to call attention to you. In quantum cosmology, you must be very careful which approach of quantum theory you must use. And why is that? This is because the equation for the wave function of the universe usually is not the Schrödinger, has not the Schrödinger form. In this case here, the kinetic term is not the usual one. You see, square root of it. It's not the usual one. And this is the source of the difference. Now, our next question is: and if the Wheeler-DeWitt equation appears in the usual Schrödinger form, and this is possible if you take, for instance, a Lagrangian where the kinetic term is in a power n. This Lagrangian mimic perfect fluid with p equal lambda rho and the sound velocities of equal lambda. And this lambda here is a constant and depends on the exponent here, n. Okay. In this framework, the Hamiltonian is just this, where this x here is just a power of the scale factor. And the wave function, the Wheeler-DeWitt equation becomes exactly a Schrödinger equation for a free particle. In this case, it has been proven in this paper here that both the consistent histories approach and the Broglie-Bohm approach agrees that there are no singularities in general, for whatever are the initial wave functions. There is no singularity. Okay, and it should be like this, because this is an equation for a free particle. The consistent history approach cannot give a different result than the Broglie-Bohm. Okay. So the conclusion on what I say is that it's wrong to say that the Wheeler-DeWitt equation does not solve the singularity problem. Unfortunately, some important people from loop quantum cosmology insist to say this. There is a lot of, now they agree that it's not true, but sometimes they continue to say, I don't know why. I have pointed out these papers to them and they agree, yeah, okay. But sometimes they continue to say these things. And why is wrong? Because when the Wheeler-DeWitt equation is not Schrödinger-like, is something different, this depends on the quantum approach one is using. When it is, it solves independently of the approach used, which is the second framework here. Okay. So repeating, it's wrong to say that the Wheeler-DeWitt equation does not solve the singularity problem. I think this is a measure very important. Right? Yeah, yeah. Uh-huh. Yeah, because you can calculate in this framework, in the Broadband framework, you can really calculate the scale factor, and you can see that. Yeah, 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 yeah. But in the case of the consistency approach, you just construct some probabilities of histories, and then they conclude that in that case, the bounce is impossible. Okay. Okay. So now I will continue with using the Broadband approach and try to formulate an interpretation for the wave function of the universe. Of course, it's something that depends on the Broadband approach. Okay, depends on this, and it's a proposal. Okay. So.
When it is Schrodinger, like, I mean, you gave an alternative. This alternative means what? There are cases in which it is not in Schrodinger form. Or
Yeah.
you can always put it in Schrodinger.
No, what I say Schrodinger form is the usual format, have a dipside T, and there is essentially only in this case. Now, not only in this case, but in the majority of cases, you have really a Klein-Gordon equation, and then you have to deal with this. Okay, you have a Klein-Gordon equation.
So in the majority of cases, it does not solve.
No, that's not no. In the majority of cases, if we use the consistency approach, it does not solve. But if you use the Broadband approach, it can solve. Even in the case, no, it can. That's the what we show here. In general, in this case, using the Broadband approach, the probability of singularity is the probability of a bounce is 1 minus probability of singularity. Okay. In general, it is like this. So you have for some type of a wave function, it's 1/2. So we have half probability of giving singularities, or half a probability to doesn't have singularity. Yes. Yes, scalar field. Yeah, yeah. Yeah, it's some scalar field, okay? With in the first case, canonical scalar field. In the second case, a scalar field with a kinetic term, power, some n, okay? So let's move on here. And so let us talk about the wave function inverse. So this is the general Hamiltonian for general relativity. So this H here is the space metric. This is canonical. This is the momentum canonical conjugated to the space metric, and phi represents all kind of fields that you can imagine. Phi represents the momentum canonical conjugated to these fields, and the Hamiltonian is a combination of constraints. Okay, H0 and Hi. H0 equals 0 and gives G00 equal T00. Hi equals 0 gives G0I equal T0I. And these other equations here gives the really dynamic classical equations Gij equal Tij. Now, if you want to quantize this, propose zero quantization, then the constraints, the operator versus the constraint should annihilate the wave function. This one here, as a very simple interpretation, is saying that psi is invariant under spatial coordinate transformation. And this one here is the so-called Weird equation, which in general is very problematic. A lot of problems we cannot solve it in general. That's why there are a lot of other developments like Leconte-Brett and all these things. Okay, but now let us continue. If you now try to say that the wave function satisfies a Schrodinger equation like this, And as H, the Hamiltonian, is a combination of constraints which annihilate psi, this is just zero. So psi does not depend on external time. Now, if you have a de Broglie-Bohm theory, so this people stop here, but if you have a de Broglie-Bohm theory, then if whatever is the equation for the wave function, it can be the Willis equation or something else. If you take the phase of this wave function, and then you can use the guidance equations, and you can say that the derivative of H is some functional derivative of the phase, the functional phase, and also for the fields. And these are dynamical equations, okay? And this is very similar to what's happened here. So one proposal that has been advocated, and I think is quite sensible, is this one by Goldstein and Zhang, and they say the wave function of the universe is nomological, it's law-like. It's like a Hamiltonian, it's like a Lagrangian. What a Hamiltonian does not exist, but it gives the dynamics. And the same thing should happen for the wave function of the universe. The wave function of the universe, using the de Broglie-Bohm approach, if you have a solution, then you have the dynamics for all fields in the universe. So it's law-like. I think this is very interesting because it's not about probabilities, because I always thought that the notion of probabilities for quantum cosmology is very weird because it can never be tested because we live only in one universe. So it's something like, I don't know, so a metaphysical thing can never be tested unless in some very special cases. And so you don't talk about probability here. So you don't need to seek for a probability measure, which is something very hard to do in general. It's natural that the equation for the wave function of the universe does not involve time. A law should not depend on time, should be a law. However, there's a missing point. We need some boundary conditions for whatever is the wave function of the universe in order to select just one. And that's what people is trying to find out. So there is the Hartle-Hawking proposal, which unfortunately does not work. The Lenking proposal. Okay. So is the proposal that this guy is made, and I think that it's very sensible, but we can construct this proposal only through the de Broglie-Bohm approach. Now, we're not about probabilities. Well, we know that we have probabilities to talk about probabilities. Well, probabilities arise in subsystems contained in the universe. So, for instance, and because in the Broglie-Bohm theory, we can construct what's so-called conditional wave functions. So let us take, for instance, suppose that the universe contains only two fields, phi1 and phi2. And suppose that you are able to find out the Bohmian trajectory for phi1. If you substitute phi1 of here, then you have a conditional wave function, which is a function of t and phi2, which gives everything you want to know about phi2. Now, under certain conditions, and this we calculate explicitly, the original equation for psi, even not being of Schrödinger-like, gives a Schrödinger-like equation for psi c. And I'll show you an example, a very important example in the following. So in this situation, when you have a Schrödinger equation, then quantum equilibrium arises, and one can understand psi's the norm of this conditional wave function square as a probability measure. And so we have this. So this is a proposal, depends on the Broglie-Bohm approach, and that's it. You can make questions. Now, let us apply this, for instance, for cosmological perturbations in quantum backgrounds. So let us now suppose that the metric is almost homogeneous isotropic, and there is some perturbations here. Okay. And so also there is a scalar field with perturbation. It's not really homogeneous isotropic. There are some inhomogeneous perturbations. And you can calculate the Hamiltonian. And you can show that the Hamiltonian has this form here. There is a first part which depends only on the background, the homogeneous background. But there is a second part which depends also on this these perturbations here. And this V here is just a Mukhanov-Sazak variables, which in this situation have proven that is the unique combination of the canonical variables which has null Poisson brackets with all other first-class constraints, generators of linear gauge transformation. So it is a gauge invariant quantity. So this is the Hamiltonian. This is the classical Hamiltonian in this thing. Now you are going to apply the Dirichlet quantization. So the wave function should satisfy this. Now I will make an assumption. This is an assumption that the background is not affected by the perturbation. And so it's some kind of there is no entanglement between the background and phi, but the background can affect V, of course. Okay, so this is an assumption. Essentially, maybe this is not possible, but this is an assumption. Now, if you make this assumption, then you can show that zero order. You can solve this equation for psi 0, and this is the same. This is the equation. And you come back to the usual quantum cosmological framework that I told you before. Then you can calculate the trajectory alpha, eta, phi of eta, and may have bounces and all these things. And then you have a solution for the background. It's a quantum background. Okay. Now we go to the second one. And now I use this notion of conditional wave function because I have solved for the background, and then I just substitute here this thing in the second order wave function, and then I have a conditional wave function. And then when you substitute back in the equations, there is a term like this, which is just if you write down the explicitly, and if you use the Bohm equation, this is this, and this is just d psi d eta. Eta is here is conformal time, but you can use other times if you want. It's conformal time. And so even if you have a Wheeler-DeWitt equation, a Caligari equation, and all these things, for the perturbations, you arrive at the Schrödinger equation for the perturbations. Okay. So this is an application of this notion of conditional wave function, which gives, even if you have a very complicated equation, in the end, for the perturbation, which is you have a Schrödinger equation. Now, so this for the modes, you have blah, blah. The difference here, this is exactly the same as the usual Schrödinger equation for perturbations, but now the A here is the Bohmian trajectory, is not the classical one. Now, usually, the equations for the modes is like this. Usually this E2 primary, even in inflation, has qualitatively this form. So you have when the universe is contracting. When the universe is contracting, this thing dominates, and so you have just a bunch of harmonic oscillators where you can give vacuum initial conditions. And then it crosses the potential, then something else happens, which is written here. So this is a solution where we are here. This is a general solution when you are inside the potential. And so this potential is qualitatively like this. It's exactly like this in the case of radiation-dominated bounce, where here there is a specific, as you asked it, there's a specific solution for the bounce. You see that there is no singularity, and it gives the usual classical expansion phase if eta is much bigger than eta 0, which is a parameter on the wave function. Now, if you do this, everything is imposing that the perturbations are in a vacuum state in the far past in this bouncing model. So these are the initial conditions for the perturbations. If you do this and you calculate everything, let me just say something. When you are in inflation, the dominant term is this one here, because this term here goes down because of inflation. But if you are in a bounce, this term here can be very big, and then in the expanding phase, this will dominate over this term here. And so when you have inflation, this coefficient is the important one. If you have a bounce, this coefficient is the important one. And then when you calculate this, we found out that the power spectrum has this form for inflation, this form for a bounce. And for inflation, you see that almost scaling inverse spectrum is for W close to -1, but for the bounce is for W close to 0. See? So that's the difference. So in a bouncing model, in order to have almost scaling inverse spectrum, the contraction should be dominated by a material wave function. Quanto falta? 5 minutes? Acho que vai dar. Now there is a challenge that just two more references to show something very, I think, very beautiful. People in bouncing models say that with a single scalar field within general relativity or extensions to it, if you have a canonical scalar field, the ratio between tensor perturbation and scalar perturbation is always bigger than 0.1 and does not satisfy the observations of the CMB, right? So the Planck satellite gives R less than 0.1. Now, what we have done, you took, for instance, a scalar field with exponential potential, which is very rich. It's a model very rich and is a very simple potential, but it's very rich. And we have shown the following thing, which is very interesting. This thing is the scalar perturbation, okay? And this thing is the tensor perturbation, this primordial gravitational waves. You see here, this is just the real part and the imaginary part, the real part, the imaginary part. And you see that both are really, well, this is the part where they oscillate. Then they get into the potential, then they increase. Note that they increase very much together. So if you have a classical system, they will stay very close one to the other. But near the bounce, which is quantum, the scalar perturbation is very much enhanced with respect to the tensor perturbations. So I think it's a very nice results saying that, showing that because of the quantum bounce, this theory can be matched with perturbation, because during the quantum bounce, the tensor perturbations becomes much bigger, increase much faster than the tensor perturbation, and you might have R less than 0.1. So as this thing here must be multiplied by Planck over the Hubble radius, must be multiplied by something like 10 to the minus 60. And then you have sigma square of the order 10 to the minus 10 as observed. And this contraction, this problem is very rich because this is scalar field because of the exponential potential. When the universe is very big and contracting, it behaves like dust, like a dust field. And then it contracts and then behaves like stiff matter because the magnetic term dominates. Then there is a bounce and it expands again. And there is, in the expanding phase, there is a phase where this scalar field behaves as dark energy, which is also very interesting, but I didn't have time to show this. So I just want to point out that it's very remarkable that the quantum bounce was fundamental in order to save this model, because the quantum effects amplify the scalar perturbation with respect to tensor perturbations, which does not happen in classical models with a single field. Okay. So I don't have time. Just I am going to the conclusions. So my conclusion is that the Broglie-Bohm quantum theory is very suitable for quantum cosmology. The proposal is that psi is homological, probabilities are secondary, it's just for subsystems. It explains in a very, this I didn't have time to talk to you, but anyway, if you want to question, I can answer you. Well, the pattern for quantum equilibrium in the very hot area may give some interesting things for the CMB, but this is a paper, well, no. And finally, it was presented a quantum cosmological effect which is the last one that I showed you, with a sizable observational consequence, which gives the ratio between tensor perturbations and scalar perturbations less than 0.1, which will not be there if the model were entirely classical, and which we have already seen. So, of course, there are many, many explanations for many models explaining that R is less than 0.1. But it's amazing that say, there's no observation of quantum cosmology. Well, if you really believe in this model, there is, and you have already observed it. Okay? I'm just want to say this just to think about it. I'm not saying that this is the model of, but you see that quantum cosmology can yield observational effect, which is this one here. Now, so in the end, just conclude, quantum theory can solve the cosmological singularity problem. You can yield sensible bouncing models. But also cosmology is a possible arena to test different quantum theories, because you see, as I was telling you before, you have different solutions using different quantum theories in quantum cosmology. So perhaps you can use cosmology to try to find something which distinguish between the many proposals for quantum theory that are in the field, okay, that are proposed in the literature. Okay, that's it. Thank you. Thank you.
Questions? I will start with the left.
Obrigado, professor, pela palestra. Thank you. Just a question on that point about probabilities and how do you define probabilities about be that the Klein-Gordon version or the Schrödinger-like versions. You said something about defining a measure for the wave function, because we know that the Wheeler-DeWitt equation renders infinite non-normalizable wave functions. So there is some step where we have to introduce. I had never understood that step, that we introduce some cutoff. I would like you to expand on the comment before you define the proposal of no probabilities for the wave function of the universe. You calculated probabilities of a bounce, probabilities of singularities, etc. How do you define the measure space to calculate this kind of probabilities?
For instance, in this simple, that's very tricky. But in this simple case, let me go back. I think you were asking about. In the simple case of a scalar field, that in the end is dominated by a connected term. You see, usually you get this. This is a Klein-Gordon-like equation, but as you don't have the potential, nothing else, then you can also define define an equation like this, okay? And it's really like a Schrödinger equation, okay? But the kinetic term here is different, right? And these guys here use these to define probabilities, okay? Because you can define a probability, a physical scalar product like this.
But this is a normalized wave function?
Yeah, you can normalize. You can normalize. If you do this trick here, go from here, you can normalize and all these things, and that's what they do. So they have to use this because they want to say probability of history, so they must have something like this. Okay.
And on the step that you go for to say that probabilities don't make sense for the universe, the argument that there is only one universe, so you can't test probabilities of different configuration, doesn't that also apply for the immediate subsystem of one inflaton? That's one field that you only don't know. The probability distribution is in initial conditions, as could it be for the whole universe?
Yeah, but see, this is a problem wherever you go. But in the case, for instance, in the case of the cosmic microwave background radiation, what people do, they in order to catch this probability distribution, for instance, for bigger wavelengths, which has this index m, if you expand in harmonics. Then you have L, and there are many other possibilities going from minus L to L, but they don't give anything different. So people integrate on this, and they can show that this must mimic this initial distribution. That's why when you see the cosmic ray background result, you can see that the predictions are really very good, because as bigger L, as bigger is this integration in M, from minus L to L, the sum in. But if you have very small L with the bigger scales, you have this, you see, the error becomes very, very big. And so that's the way they circumvent this problem in this case. But in general, you have to think about it.
Thank you for your nice talk. I have a simple question concerning the time, because in the standard with the DeWitt, there is no time because the conjugate momentum is 0. So you have time, but this time, is this related to some algebra of commutators? So you should have, can you think this as a generator of some transformation, or is something outside that we are somehow putting into the game? But no, you see what I mean?
Yes, yes. Now, look, if in the Brightborn approach, if you say that, well, we stay with this media superspace where the geometry is almost homogeneous and isotropic with small perturbations, the time there is just a parameter time in the same way as general relativity, just a parameter time. But if you want to think about the whole thing, then we have made a paper. I've got something here. With something. And we have shown that in the full picture, then this notion of time is really, really very different. And we have shown that there are some preferred reference frames. There are some preferred reference frames which this theory gives.
Thank you. The question is regarding the tensor to scalar ratio. So your model agrees with the observation. That good for you. But there are other models like ekpyrotic and the models of Steinhardt, right? They also
model inflation agrees also.
Sure. Yes, yeah, lots of models, right? So, but in some of the models of ekpyrotic, it is absolutely 0. It is 0. It's not just less than 0.1. It is 0. In your case, is it 0 or it is?
No, it's not 0. It's something, but and
non-zero.
What is the here depends on the parameters, but is small, but depending on the parameters, it could be observable in the future.
Okay.
And
so the question is, tomorrow, if the observations come out, you can still tune your theory to fit the observation, right?
Yeah. Okay. But just something that is important, I think it's always important that, well, I think I showed this here. This bounce is about 10 to the 4 Planck lengths, okay? And I think this is important because I don't have confidence in this Wheeler-DeWitt approach if you're really very close to the Planck length. Then I think there we should do something else. But as it's not really so close to the Planck length, then I think we can use this Wheeler-DeWitt approach and then make some calculation. And as the bounce never reach the Planck length, but just something in this case, 10 to the 4 Planck length, then I think we can.
Got it. Thank you.
First of all, thanks for the lecture. So my question is very simple. On the previous slide, this is one, you show the graph. And I just want to know how you make the calculations to run like 100 orders of magnitude.
This is it's just a program that we use, but there is this can be done, and you see, well, what is showing here? This is showing that when you are there, the universe is contracting, and the wavelength is much bigger than well, when this thing is much bigger than this, the two solutions just oscillate in this. And then when this thing becomes smaller than this, then they begin to increase. And here, during the bounce, there is augmentation of scalar perturbations. Now, there's a problem. If you want, I can show you. It's very detailed thing that I can show you if you want.
Okay,
After.
thanks.
More questions? Okay, let's thank Nelson Quintaneta. We'll be back at 2:00. Yeah, that's it.
Convencido de tudo?
Peraí, tem que ir no banheiro, tá louco de
Vai lá. Peraí, deixa eu desligar.
Vai ficando mais.
Bom, oi.
Good afternoon. Then we have the pleasure to have Professor Bini. He will talk about gravitational scattering of binary system, recent developments, and we have 1 hour.
Thank you very much, first of all, for the kind invitation to Professor Novello, Professor Moschella. And what I'm going to introduce you is what is fashion now in post-Newtonian, post-Minkowskian approximation when discussing the features of the binary system. I'm only interested in analytic results. And let me say that we are now entering really after so many years, more than 20, in which we explored everything concerning coalescing processes. We are entering the scattering situation. And this is a very rich new field in which we had contributions from high energy physics people too, not only people working in general relativity. And there are, of course, new results, which I would like to introduce you. So, binary system, the main motivation is that these are the pillars of the gravitational interaction. Okay, but then you have to solve the Einstein's equation, and this is a big task. It is hopeless to find exact solutions, and then you have to use some approximation method or numerical relativity when available. So you have to solve Einstein's equation sourced by the energy momentum tensor associated with the 2 particles, which are represented this way, like dust, but with the presence of the Dirac delta function. This dust is located just along a single Ward line. Okay. So when you have solved somehow by using an approximation I'm going to discuss Einstein's equation, you can reconstruct a metric, find the geodesics, express the geodesics in a Hamiltonian form. In the end, in the conservative case, you have a Hamiltonian system. And if you want to add the radiation reaction effect, they enter as an extra force to the systems of Hamilton equations. The idea is use whatever method you want, extract the gauge invariant information, and then convert from one point of view to the others. So there exists a list of tools, which recently we would say they work in synergy more than in competition. There is the famous post-Newtonian approximation here. Post-Newtonians means weak field and slow motion. This is fully known up to 4pn, so V8 divided by speed of light to the 8th power, which is equivalent to 4 loops, fully known. There are partial results incomplete, because there are 2 unknown still at 5pn and 4 more unknown at 6pn. This is the status of the art in post-Newtonian approximation. With the difficulties I'm going to briefly introduce you. Then there is the post-Minkowskian approximation, which is actually an expansion in weak field means just an expansion in the Newton's gravitational constants. Okay, the metric associated with the binary system in a post-Minkowskian approximation is explicitly known only at 2pn. Then recently, in the last 3-4 years, we have seen results coming from different approaches in which one has all the conservative aspects, let's say a Hamiltonian, available at G cube and at G4. And the next challenge then is G5, but concerning the radiative losses, energy, angular momentum, and linear momentum, we are not at the same level. We are incomplete at G4. Okay, then there are other formalisms which maybe we can summarize saying that they conveniently use any new information coming from post-Newtonian and post-Minkowskian, post-Minkowskian approximation. The most important one is perhaps the effective one-body approach, introduced in 1999 by Alessandra Buonanno and Thibaut Damour. And actually, what is known in the other approaches is also known in the effective one-body formalism. Perturbation theory instead is transcribed here under the name of a gravitational self-force. Gravitational self-force is actually black hole perturbation theory. Self-force or self-torque in this case. I mean, when you work in perturbation theory, first of all, we know only analytical results concerning linear perturbation. And the linearity means linearity in the mass ratio. The mass of one body is much less than the mass of the other one. And this is the parameter with which the expansion is carried on. Okay, so, but the advantage, so there is a problem. We cannot go at higher power in this approximation analytically. So we remain at the level of linear perturbation, but we can go high PN. And indeed, some 10 years ago, we started this competition. Now there exist results at 22 PN, at least for certain quantities, which is too much, but you have to imagine that as soon as the PN approximation level increases, a number of effects enter in this discussion, and having the possibility to compute all together is a big advantage. And gravitational self-force, let's say, has played an important role starting from 2013. And then there is multipolar post-Minkowskian approximation, which is the way in which we treat a binary system, considering a near region and a far region, and then matching together these two regions, which has produced the waveform, let's say. And now this is tested with the other approximation techniques. So fashion of the moment is the amplitudes. If you consider a scattering of two particles, the gravitational scattering is not much formally different from any other kind of scattering. So all high energy people in the last 3-4 years have been starting computation in this field and produced interesting and new results. Still incomplete, but there is a good trend, I mean. Okay, let's examine briefly. So in 2019, Zvi, Bern, and collaborators show that the 3 PM G cube Hamiltonian of the binary system can be written in this way, where you see the free energy of the two bodies in the center of mass and the interaction potential, which is an expansion in powers of G with coefficients which can be listed. Okay, it's readable and it's easy to play with. Then the game started, and the same authors in 2021 published the 4 PM Hamiltonian, which is now less readable. I mean, there is a full page of coefficients involving transcendental functions, polylogarithms, etc. Concerning the radiation, the radiation reaction, there are partial results obtained by Rafael Porto and collaborators at the beginning of the current years. And this is the status of the art. So the 4 p.m. is still incomplete in the sense that the radiated angular momentum has not been derived yet. So I was really surprised in 2019 when looking at this Hamiltonian, because the previous result, the G-square level of approximation, was known about 40 years ago. And if you look at this result, the metric associated with the binary system is enormous. All quantities entered in this expression have retarded effect, involve nested functions one into the other. So it was really an important result, the one obtained by Zwibern and collaborators. Unbelievable at the beginning, but now fully appreciated and well known. Post-Newtonian. Post-Newtonian, as I said, is an expansion in V over C, and equivalently, it requires also small field. I mean, Gm over R should be small. So we are enough familiar with this Hamiltonian at the Newtonian level, and then at the next levels, 1pn, 2pn, etc. Sorry, it is corrected by terms which actually are polynomial in this quantity nu, which is called the symmetric mass ratio. Mu is the reduced mass of the system, nu is dimensionless, is the symmetric mass ratio. So we are at the beginning now. The 1pn Hamiltonian uses one line. There are boxed terms. I come on this in a moment. And a couple of lines are necessary to express the 2pn level of approximation. 3pn can be still written, but you see, you are losing the possibility to perform analytic computation without the help of an algebraic manipulator system. There are characteristics, interesting characteristics. For example, we see that as soon as the Pn level increases, the symmetric mass ratio enters with higher powers. So 3Pn, new cube, polynomial structure, interesting. Then there is the appearance of pi square, the beginning of something which is transcendental. But when you go at the next level, the Hamiltonian becomes much more involved, even in the center of mass. It has two pieces. One is local and uses a full page now and contains all the structure I mentioned above. Now we are polynomial in the symmetric mass ratio up to nu to the 4. And the transcendental structure survives. And you see, besides this local part, it appears something which is unfamiliar for us. It's a non-local part of the Hamiltonian at 4pn, which depends on the full history of the system. And these effects then beyond 4pn are the main difficulty of the problem. Okay, so here I sketched only the relevant formula. This is the quadrupolar moment of the system, which appears with 3 derivatives, and inside this non-local integral, which also has an absolute value. So you understand that doing analytic computation starts being a big problem. But anyway, at 4pn, everything is known and has been checked by different families, let's say, or people working in this context. It has been first obtained in ADM coordinates, Arnowick, Deser, and Misner, and then converted in effective one-body formalism by Damour, Yaranowski, and Schaeffer. Some year later, harmonic coordinates results were available due to Luc Blanchet and his group. And finally, after a while, also effective field theory produced and confirmed the same results. So you have this Hamiltonian available with different choice of coordinates. And really, they are equivalent. So if you don't like effective one-body formalism, it is just a coordinate choice. So it's nothing more than this. I mean, all these Hamiltonian or Lagrangian corresponding are canonically equivalent. Use what you want. We don't care. Let me say something about the effective one-body formalism. So the idea is, we know from Newtonian physics that if one can disentangle the motion of the center of mass, then there are simplifications in the Hamiltonian. And the starting idea was, let's write the complete Hamiltonian of the system in terms of an effective Hamiltonian, which uses several potentials, okay? So A is a function of the inverse radial variable, this U, which has a new structure as we have seen previously in the PN expanded forms of the metric. It's the main radial potential. Then there are radial potential. This is the bar D. There are Q powers of PR. You look at this expression and you immediately recognize that it's more natural to study systems in a coalescing phase because it depends mainly on powers of the radial momentum. So along circular orbits, all these terms disappear. It is compact. And there can be an advantage splitting all the Hamiltonian we have seen previously at 3pn and 4pn in several potentials. This is really convenient because the Schwarzschild terms, here, the Schwarzschild terms, the boxed in red, are what is needed only to deal with the 1pn. So just a couple of potential, but one is trivial. If you go beyond at 2pn, you need to add these two terms, just these two terms. Let me remind you that at 2pn, the explicit Hamiltonian, not summarized in terms of this potential, was using a couple of lines. And at 3pn, which is the one I show here, you have to add three more terms. So the idea of this effective one-body approximation is that the original Hamiltonian I showed you at the beginning contains terms which are actually the Pn expansion of something which is given by the square root we have seen, in which it's written the effective one-body Hamiltonian, but not really much relevant. What is relevant is the content of the potential. That is, in these three lines, I have everything, okay? So there are computational advantages. You can use closed form expression and inject at the very end the coefficients of this expansion. And so the number of coefficients which are needed is strongly reduced. But good things are going to finish soon, because at 4pn, we know the Hamiltonian has to show a local and non-local part. So all the EOB potentials has to show a local and non-local part. So much better than in the previous case. I'm selling what I can, but still rather involved. Let's examine. Now we recognize the polynomial structure in the symmetric mass ratio is okay, but the transcendental structure is enriched beyond the 3pn, where we have seen the appearance of pi square. Now there is Euler gamma and logs. Okay. And this transcendental structure, higher, when you go higher and higher in post-Newtonian approximation, enriches more. You will see the appearance of a Riemann zeta function, 3, 5, etc. Also, there are these logs. U is the inverse radial variable, so they appear now starting from this level. This is the sum of local and non-local. This is the complete expressions, okay? But this is all that is needed, still half a page. So big computational advantage, but thanks to this, we understood that going beyond is possible. You need just to increase the number of terms in the various potential and the number of potentials which are needed to reach the prescribed accuracy. So we can work in parametric form. In this way, it's convenient in EOB because we can leave a number of unknown coefficients, which is much, much less than when you are working with the fully expanded Hamiltonian. And then if any other formalism can compute some gauge invariant quantity, which I can compute in EOB, then I fix this coefficient. And this is a big improvement. Okay. Okay, so the status of the art is that we are now at 6pn, incomplete, in the sense that there are still 6 coefficients which we were unable to determine by using perturbation theory. Okay. The method which we have been using recently, 2020, 21, etc., has been called tutti frutti because it combines information coming from any context and translate conveniently in EOB. Okay. Again, we have the problem to determine local and non-local part. But we are looking for what can be helpful in this case. The first tool really helpful has been gravitational self-force. In 2013, me and Thibaut were able to complete the 4pn approximation by computing the last missing coefficient. Gravitational self-force is black hole perturbation theory, as I said. So it's beyond the scope of this seminar to give details, but let's summarize only because we are all familiar with this. Start with the Schwarzschild metric and write down gravitational perturbation. So decompose the perturbed metric in spherical harmonics. So you remove the angular part of the perturbation because it goes with the spherical harmonics. Then you are left with 2 variables, time and the radial variables. Fourier transform in time, and you are left only with the equation depending on a single variable, the radial variable. And this gives what is called the Regge-Wheeler-Zerilli equation, a sort of Schrödinger-like equation, which it's a big accomplishment. Okay, you have succeeded in separating all the other variables, but now you have to analytically solve this equation. Otherwise, it's nothing, okay? And solve this equation means there are source terms. These source terms are due to the perturbing objects, the particles. They carry Dirac delta functions, okay? And for instance, if the perturbing particles is moving along a circular orbit, these Dirac delta functions have actually played the role of considering only a single frequency because you are circular. Okay, so the spectrum of this perturbation, it's easy. It's reduced to 1 frequency. The main difficulty is that when you go beyond the circular motion, then eccentricity plays a role. If you consider an expansion in eccentricity, a small eccentricity, you can proceed because you are circular, derivative of Dirac delta, you are first order in eccentricity, second derivative of Dirac delta, everything helps, okay? So quasi-circular motion can be treated, and we actually did this. The other problem is that, okay, this is a sort of Schrödinger-like equation with source term, which have Dirac delta function. So you need to use the Green function method to solve this equation. And then you need the solution of the homogeneous equation. You need the post-Newtonian solution of the homogeneous equation. Okay. Then imagine that you have done this. There is a technology due to Japanese people, Mano, Suzuki, and Takazushi, which for a given value of the L number allows you to compute the solution at the level you want. So if you need to go at 22 PN, you need to take some 40 multiples, L up to 40. The problem is that then you have to perform the summation. M, the magnetic number, should be summed analytically from minus L to plus L, and L should be summed analytically from 0 to infinity. And this is not a trivial task, okay? There are relations one can use, and there are other difficulties. For instance, when you simply resum over L, the series is not converging. So you have to regularize the series. You have to remove what is called as the self-field, okay? And then there are additional difficulties. For instance, the multiples corresponding to L equals 0 is the addition of mass to the black hole. This is a gauge problem. L equal 1 is the addition of rotation to the black hole. And this is a problem too. It's a gauge problem. After this, if you are able to perform all these steps, you have to compute a gauge invariant quantity. For our situation, we started computing the redshift of one of the two bodies. And then over the years, we computed also these other things, the periastron advance, some gyroscopic precession. And then, as I said, we had to convert in the Hamiltonian, but this is easy because these are gauge invariant quantities. I compute them with the Hamiltonian with the known coefficients and fit this coefficient with the analytic results. So let's say in the last 10 years, we have been exploring redshift, periastron advance, frequencies, etc. And now we are at the problem of the scattering angle. So we are now passing from coalescing processes to scattering. We are passing from a spectrum of perturbation with the finite number of frequencies to the scattering, which has, by definition, an infinite number of frequencies. What was previously a summation is now an integral, and the difficulties are still there. The strategy is always the same. I mean, for instance, the redshift, to be more explicit, consists in computing in perturbation theory this U1 dt d tau, which is then converted in Hamiltonian formalism because the redshift is the derivative of the Hamiltonian with respect to the mass of the body. This has a name, but we are not interested in giving details. So you know what I can do. So for Tutti Frutti, we had to compute, to reach the accuracy level at 6 PN, we had to compute perturbation along a centric orbit, including correction to the eccentricity up to eccentricity to the 8. A month. You do only this in a month. And the result appears in this way. Okay. The conversion in useful information was due to this first law of binary black holes, which Luc Blanchet, Bernard Weining, and Alexander Letiec found just in these years. Okay. To give you an idea of what comes out, log now becomes log square, and there are all the transcendental structure I was mentioning above. conversion in EOB potential is straightforward, but the structure is kept. And then this is how you see this result of perturbation theory. I was able to perform computation using Maple up to 9.5 PN, let's say, and this guy, Chris Kavanagh, for one of the potential reached by using Mathematica the incredible level of 22 PN. Okay, so you belong to the machine when you do this kind of computation. Okay, you or trust or not. Then you can do checks with numerical relativity, and the checks are the most important part, because we can reach the accuracy of keeping a certain number of digits, and then we believe to the results. So in this way, we have obtained information first on the non-local part of the EOB coefficients, and then we could subtract this non-local known part to obtain information on the local part, but we were limited to the range of validity of perturbation theory. Let's say linear perturbation. Only the terms which are linear in the symmetric mass ratio. The next challenge, second order perturbation theory, has started, but has only produced up to now numerical results. But analytical results will come. Okay, it's just a question of waiting some time. So there remain a number of coefficients which we could not obtain. All these involve higher power of the symmetric mass ratio. So you can understand, you can work at 10 PN, but if you have a number of unknown coefficients, which is enormous, you have not done anything useful. And then the scattering angle has allowed us to compute mostly of this coefficient up to 6 PN. So here again, what remains to compute, and then the picture which you see the solid circle, if you read in this way, are post-Newtonian information. If you read in this way, since U is GM over R, are post-Minkowskian information. Okay, and here you see the structure in U of all the rows. So when you find a white circle, there is some unknown up to now. Okay, this is where we are. Let me say better. At 5 PN, we have been able to compute 95 coefficients of 97. 2 are missing. At 6 PN, we could fix 147 coefficients of 151. And now let's start talking about scattering. Scattering is just another gauge invariant information concerning the motion of a binary system. Okay, so we can have local aspects, non-local beyond the 4 PN, we know they exist. Conservative aspects, if you study the conservative dynamics. Correction due to the radiation reaction force, which starts at 2.5 PN and appears. We can work in the time domain or in the frequency domain. Okay, and we can compare with results coming from other constants, other formulas, sorry, other kind of computation. Okay. First of all, if you are with the system which is not conservative, as I said, it appears only an external radiation reaction force to be added to the Hamiltonian structure. Okay, you can, if this force is known, determine completely the motion and determine the scattering angle, because if you work in a polar coordinate, then you have d phi d tau, the scattering angle is to look at phi at minus infinity and the plus infinity, subtract the two values. This is what comes out. There are explicit formulas, but the situation is this, okay? When there is a radiation reaction, this picture is slightly modified. Like the periastron advance, it rotates a bit, but nothing more than this. And if you want, in the conservative case, there are ready-to-use formulas, which you can use. You compute the radial momentum and integrate over the orbit, parameterize, for instance, by using the radial variable, differentiate with respect to angular momentum. Everything here is scaled, it's dimensionless, but it's a trivial task. You have the energy, then from at the Newtonian level, for instance, you isolate PR square, take the square root, expand, insert, integrate, differentiate with respect to J. You have the conservative. It is done. And this is what we did up to 4 PN, as I said. Now we want to convert this information in something useful. And we discovered that indeed, the non-local part of the Hamiltonian, which was the worst, the main difficulty, was the one we could compute easily, in the sense that we have integrals of this time to compute. There is this absolute value, which is critical, but doable. And then nothing works, in the sense that these integrals you can do only numerically. So I tried myself for a month, and Mathematica, which is much better than Maple to compute integrals, gave me only 15 digits exact. This is not enough to fit with something. There are fitting routines like the PSLQ algorithm. If you know the results as a structure, I mean, as a coefficients time log of 2, coefficients time gamma Euler, then you fit these results and you discover this coefficient. But with 15 digits, you cannot do too much. So we went knocking the door of high energy physics people, those doing similar computation for quarks, for gluons, etc. And this was Stefano Laporta, famous because he has also an algorithm which carries his name, and Pierpaolo Mastrolia. In 24 hours, they gave us a result with 256 precise digits. Then they fitted somehow and produced the result. After a while, this was Stefano Laporta, after a while, Mastrolia was able to prove analytically that this was the result, playing with the harmonic polylogarithm, etc. So the structure now is richer. As you see, there is zeta3, but this is already appearing even before, but there is the Catalan constant, which when you put all the terms together, disappears, but it is a signal, it's there. Okay, this is the NN law accomplishment and the way in which has been obtained the results. You introduce in the function some parameter, differentiate, integrate Ala Feynman with respect to this parameter, and reconstruct the final result. And if you want to go beyond, then you need more involved integrands, some blocks of this time, but 300 times this block. T prime and T are the variables, which they could numerically integrate with enough number of digits and fit the results. And so I was thinking, my job is finished, because now if we want to go beyond, we need this expertise. Okay, this is a possibility. But then somebody said, if things are becoming so involved in the time domain, let's pass to the Fourier domain and see if things simplify, even if you may say there is a conservation of difficulties. And indeed, this is the case. When you go in the Fourier domain, you have the possibility in this case now to expand in powers of G. As I said, we are interested in powers of G, post-Minkowskian, okay? And this is large eccentricity or large J. Okay. The main difficulties in this case is that you have to do with the Bessel K function, the famous Bessel K functions that Prof. Moschella showed yesterday, with an order, this P, which is the same variable U divided by eccentricity. So the integration variable appears as the argument and as the order, but you can expand. So if you go large eccentricity, this P is 0. Okay, the first step is doable, but then there appears the derivatives of the Bessel K function with respect to the order. And this is, I mean, not an easy task, at least for what we know. We were able to compute a lot of these terms, but you should know, in advance, we knew the form of the results, perhaps this has been playing a role. Then we were using Melling transform, several tricks of exchanging derivative with integrals, etc. At the end, we obtained the results. But again, we cannot go much beyond, because in this, which is considered the person, the most expert in this field, in 2016, said that only up to the third derivative, here I showed the second, but up to the third derivative, it's known, no more. But look at the second derivative with respect to the order. It's a mess. I mean, you have hypergeometric function. You have Meyer G functions. Just coding these, it's a big task. So here we are. We reach the same level of difficulties as in the time domain computations. But this was enough to use all the results we could obtain, because the scattering angle as a gauge invariant variable has a new structure by itself. So knowing that there should have been terms with a certain polynomial degree in nu has allowed us to kill all the extra coefficients. If we know that this term should be quadratic in nu and no more, we kill all the rest. And this is an information we used to determine certain coefficients in the EOB metric. Okay, let's say this. Of course, this result, this polynomial structure, was obtained by Damour in 2020. And using the new structure, we could compute with still some unknown, but at a higher PN level, the various coefficients of the new structure. So if you compute the scattering angle at G square, there involve only quadratic expression in nu, okay? And so you can kill, if you have generic expressions, all the cubic, quartic, etc. These are relations among unknown coefficients, which allow to fit few of them, okay? Okay. And now we cannot do more in the conservative case. Let's pass to the radiation reaction situation. In the radiation reaction situation, many years ago, in 2012, we produced this simple formula, which is a sort of Taylor expansion, but a sort. There is this 1/2 factor which plays a role. I mean, it's not actually simply a Taylor expansion formula. It uses the symmetries of the problem, but if you know for your system the radiated energy, the radiated angular momentum, and the conservative part of the scattering angle, you can determine the radiation reaction part of it. Okay, at least under certain under certain conditions. After a while, this relation will be no more valid. For instance, if the center of mass starts moving, this was not taken into account, because then you should add the loss of linear momentum besides the energy and the angular momentum, which complicates things, but doable, I mean. Now this relation is known as linear response formula. Okay. And what happens recently? Recently means this year. March this year, Amplitude people, the name you read here. So let's say Stefano De Angelis and Gabriele Travaglini, the first group, Radu Roiban, Carlo Heisenberg, etc. Three different groups arrived saying we have computed the scattering amplitude at order G square. At order G square, radiation reaction effect starts. So an important result. They all agree among them. Passing from these post-Minkowskian relations, it's not really an easy task because they involve very large expressions, and Mathematica cannot be helpful, and Maple less than Mathematica. So you need to deal with them with some tricks. Also, these expressions have their own complications. So there are spurious poles, the building blocks are so large. Just to show something. This is the result, a sum of terms. Each term involves beast of these types. Okay? If you want to use the results, we need to convert Pn. But imagine that every variable here has a Pn expansion. And we need to go IPN. We cannot stay at the Newtonian approximation. We know everything at that level. We need to go 5Pn, 6Pn to have some. Okay, after a while, and a while means the full summer, we arrived at the conclusion that these results are incomplete in the sense that they partially reproduce our post-Newtonian knowledge. Partially means that perhaps they have estimated a few integrals, maybe differently from what is needed, or simply they omitted the evaluation of several integrals. Okay, then we informed these people. These are computational details, but you don't need this. Because the amplitude result, this M, converts in multipolar post-Minkowskian formalism, quadrupole, octupole, hexadecapole, etc. So these are equivalent information. You have to disentangle, which is not an easy task, but in principle, this is doable. And then each of these blocks, if you compute in Pn sense, as a structure, you have the ordinary quadrupole, then there is the tail, then there is the memory, then there is the tail of the tail, then there is the tail square, etc. All this contribution to be consistent at the level of approximation we need should be computed and then compare with them. Okay, so we realized that there was a difference. So we agree at a certain level. Let's say at 1Pn, we were happy to see our exam Newtonian, okay. But at the level in which we are really interested, there are still discrepancies. So these discrepancies we summarize in this way and fitted from our Pn knowledge to be summarized in this form. Okay, then we started looking for checks. For instance, in the limit of frequency small, there are general results. This is the soft theorem due to Weinberg, which should be satisfied. And their expression was not in agreement with the soft theorem. So we started believing maybe multipolar post-Minkowskian has more information, is correct, whereas there is something missing. So we could obtain the expression for all these coefficients in the soft expansion. there are prescription for these coefficients in the literature, and we could check. We agree. And then what is happening in these days is that the three groups have produced additional terms, which perhaps have been obtained, including the evaluation of certain integrals, which was omitted previously. These terms are as large as the previous one. So this is not a small correction, it's something. And we are testing this now, currently. Still, to what I can tell you, there are differences. So the story will continue. This is the way in which we could test what is known. But we know that, from amplitudes, we can receive a lot of information. The GR community is enriched by all this new information in the last 4 years due to the amplitude community. These are their names. And we also know that physics is incremental, okay? I prepare the land for doing further comparisons, computing what is necessary maybe at G5, because this will be the next challenge. And that's it, in the sense that now the main, the scope of all that kind of research is to reach a final agreement between multipolar, post-Minkowskian formalism and the amplitudes. Big task. We want to have information on the scattering angle from cell force. As I said, the spectrum now is infinite. And this is a big difficulty. I mean, the number of integrals one has to compute analytically is enormous. And you still belong to the machine. For the moment, we are computing, I'm going to finish soon. We are computing scalar cell force along hyperbolic. Then we should multiply by 10 to have the gravitational perturbation. And then we go to the non-conservative aspects. I mean, we want to know more information about the non-conservative aspects introduced by Rafael Porto and the co-workers to use to find this complete agreement and fixing all this missing. So final comment. I'm using Maple. I find it exceptional to work with the general relativistic expression. Tensor calculus is trivial with Maple if you have an explicit metric. If you have not an explicit metric, it creates enormous amount of terms, and this is. But this is not enough, because there are integrals Maple is still computing, and Mathematica computes after a while. So we start using Mathematica also. This means people generate expression with Mathematica. We convert to Maple using the routine of conversion. And maybe if we did everything correctly, we will see. So the wisest thing is to have always a combined use of all these tools and also of numerical estimates. Maple has other problems. If you ask Mathematica, expand this quantity up to this level, Mathematica uses all the necessary time, but then generates this expression up to that level. Maple, no. If you say series up to this, it puts down. If the series starts with negative powers, then it truncates before. So this forces us to put flags everywhere, to check that the terms we were supposed to compute have been really computed. And this makes the programs more involved and slow, etc. But I don't know other way out. So thank you for your kind attention. This is all that.
Questions?
Thank you for the talk. I have some questions about the gauge invariant quantities you defined many slides ago.
You want to see this, or I can
yes,
tell
please.
you what they
Sure,
are?
sure. I can tell you. So the redshift, you seem to be defining this different from my understanding of what redshift is. What's
You have
redshift?
two bodies.
Sure.
The redshift is the ratio dt d tau
Mhm.
in the 4 velocity of each of them.
Mhm.
So is the
So
t component of the 4 velocity of one body.
It's similar to Doppler shift, like what I can think.
Exactly.
So in
And
that
then there exists this first law of binary black hole dynamics,
Mhm.
which converts the redshift in an operation to do with the Hamiltonian.
Mhm.
This has been done by Blanchet, and it is derivative of the Hamiltonian
With the
with
mass.
respect to the mass of the body.
I can see.
If you use a Newtonian Hamiltonian, you can check this as an immediate result. It's very simple. And all the gauge invariant information have a transcription of the same type, let's say.
You also list the orbital motion or the orbital velocity or frequency also as one of the gauge invariant quantities. Aren't they redundant with the redshift?
Let me be more precise. If you express these angular velocities in terms of energy and angular momentum, they are really gauge invariant. And this is the way in which I was using this information.
Mhm.
And it's easy to understand because energy and angular momentum are. If you instead express this quantity in terms of semilatus rectum and the centricity, okay, the number is the same, but then you are using objects which depend on the coordinates, because the semilatus rectum in harmonic coordinates is something, in EOB coordinates it's another point. So you can be consistent if you work within a single coordinate system. The number is always the same. If you want to see explicitly the gauge invariance of this object, then you have to convert semilatus rectum and the centricity into energy and angular, and then it's trivially.
Last question. For comparing with the current LIGO, Virgo waveforms, what is the minimum number of, let's say, PP and R?
I can tell you what I know, in the sense that our 4PN Hamiltonian is implemented in LIGO, okay, fully.
Mhm.
The rest going beyond only partially, in the sense that they have numerical simulation, they fit certain parameters, they use them comparing with the numerical simulation, they put numbers, which is much more convenient.
Thank you. I will talk to you later.
I'm here.
More questions? Okay, let's thank the person. Okay, now we'll have Professor Bonanno, who will talk about spontaneous break of diffeomorphisms invariant in quantum Einstein gravity. Okay, let's take a break of 5 minutes because people were asking me to take a wait 5 minutes.
Yes.
Okay.
Yes.
Okay.
Okay, thank you very much for the invitation. I would like to thank Professor Novello and also Ugo for suggesting my name. It's always a pleasure to come here after many occasions. That's not the first one. Actually, I'm happy to say that when I was a graduate student, I was attending one of the school organized by Professor Novello. So it's really a pleasure to be here. So this talk is something which is related to a work that I've been recently doing with some students in the University of Insubria and some collaborator in Catania, which has been recently published. And the question is has something to do with the dynamical breakdown of diffeomorphism invariance. We all know that there is a metric in this space-time. Okay, we call it Euclidean metric, Minkowski metric, whatever. Okay, but the question is whether actually, from a quantum mechanical point of view, this question makes sense at all, in the sense that we might have a situation for which, because of quantum fluctuations, this was not the case. For instance, in the early universe, we might not even have the geometry to discuss this possibility. And this is the topic of my talk. What is the real phase structure of the space-time? So I will discuss the general problem of phases in gravity. Then I will concentrate on conformally reduced gravity, because it's simpler, but it has all the elements we need to understand the question from the very physical point of view. I will discuss an example, which is r plus r squared gravity. And then I will discuss a general f of r example. And I will present some new results about the ultraviolet critical manifolds in quantum gravity. And then at the end of my talk, I will come to the conclusion discussing what do we mean for a phase of unbroken diffeomorphism invariance. And I will also say some words about gauge invariance in general. So let's first keep the discussion as simple as possible, but of course not simpler. So in principle, so is there any, does it work? Oh, this way, okay. So in principle, one would like to write at the quantum level an equation of that type, which will mean that this is what is realized in nature, because we have broken the diffeomorphism invariant. There is one particular metric, one particular space-time, and this space-time is the space-time we are living. We are now discussing in this room, okay? Then the question is whether there is actually another phase which is characterized by the fact that mean value of the geometry is 0. This will be a pre-geometrical phase, a phase where there is no manifold, a phase where probably we can only use the notion of topological manifold, not differential manifolds, okay? And it's very difficult to understand this type of the structure of this type of geometry, of course. What do we mean for something which is we cannot make even a derivative of something like that? But then there is also another problem, which was pointed out by work by Kolyakov in '93, This statement here is not gauge invariant, of course. The order parameter itself is not gauge invariant. So one possibility is to consider, oops, sorry, this is, well, this not this quantity. If I do a gauge transformation. Yes, coordinate transformation, but I mean, actually it's here, this statement is not gauge invariant. That is what I'm saying. Any statement that you make on the metric is not gauge invariant because the metric itself is not the gauge invariant quantity. So in principle, you would like to write something like that, but the order parameter itself, if you do a coordinate transformation, of course, is not gauge invariant. I'm simply saying this, and so some people propose to use an expression of this one, of this type, which is analogous to the Wilson loop in QCD, which can be thought as an order parameter, or another possibility is to use the mean value of this other operator, which is basically also something which, if you average, I mean, this you have to imagine that you are averaging over all possible metric. These things will also be a good candidate for a gauge invariant quantity, but of course it's very difficult to compute something like that. Even if you talk with people on lattice, it's not something simple. But we have some intuition in this case because we know at least how it should behave from the heat kernel theory for a small spacing limit of the propagator. We know that this quantity, if this, for instance, is proportional to the say in the Euclidean setting will be the delta mu, then you will expect that that quantity will scale in this way for L very small. This is the dimension of the space-time. Okay. D is B was what was before this quantity. This is the mean value of the exponent of this quantity. Okay. Okay, then if we are in the pre-geometric phase, of course, that this will be on the average 0, and you will not see any change with the distance of this quantity. So in principle, you try to use this as an order parameter. So, and then the question is, how can we detect this scaling behavior? How can we do that? So the question is, of course, very complicated. So let's imagine for the moment we consider only the conformal degrees of freedom. Let's say the scalar degrees of freedom in gravity. That means the following, that conceptually, that's not very different. What we would like to do to write a quantum effective metric, we would like to perform a path integral around the background metric, and we have to choose that in order to make actual calculation, and we want to integrate out fluctuations h mu nu around this background. Of course, the background cannot be chosen freely. We should, in principle, try to make a wise choice of the background so that the mean value of the fluctuation around the physical background should be 0, as in the case of background field method. The key point is that any physical length must then be proper with respect to the background metric. So in the conformally reduced theory, what we do is the following. We imagine that the background metric is given by some quantity, which is, this is a genuine quantum field, times some fiducial metric that we just use to make practical calculation. Our quantum things is this H2, is chi2. So we would like then to quantize the theory. Imagine we have an action for chi, and this action we will specify later, Basically, this is the fundamental field we split in a background part plus a fluctuation. So in all this discussion, this chi plays the same role of a microscopic metric in the full theory. So the expectation values f bar of f and phi of chi bar of chi plus f bar are the analogues of h bar mu nu and g mu nu, which is the main the expectation value of the microscopic metric in the full theory. What we would like to do, we would like to find an effective potential for this quantum field so that at k equals 0, if there is a non-trivial minimum, then we say that we have broken diffeomorphism invariance, because a non-trivial minimum is basically here. If we go to the expectation value, then we can imagine that at least this is a toy model of what will be the breaking of diffeomorphism invariance. Anyway, let's now go to an example so that we can understand what I'm talking about directly from the equations. So imagine we have an equation of this type, of course, in Euclidean signature. So that is Einstein-Hilbert equation plus R squared. Imagine we define this Weyl rescaling, where nu is this actually in d equal 4 is just 1, and this g hat is a reference metric. Our scalar R, as everybody knows, today we already had some talks about that, behaves in this way, and therefore, okay, oops, spoiling, okay, and therefore our effective action is the following. You have a phi box phi term, the hat is in the reference metric, plus some potential. This is what we are interested in understanding. Then we have a box square term, of course, because we have included this R square term, just to make life more complicated. No, there is a reason why I'll discuss later to that. And then we have this coupling here. Okay, this R hat is the Ricci curvature of our fiducial metric that in the following discussion, I will decide that is just d-dimensional sphere, but I can in principle use any other fiducial metric I want. Okay, so now the potential, it is basically composite like phi square in d equal 4. This is phi to the 4 term. And then you have this term, which is basically constant in d equal 4. Okay, and now this z here is usually related with, it's a running quantity. You see that you have this k because they are usually function of the cutoff. They will evolve because of quantum fluctuation. So this is really a running potential. We would like to see what happens at k equals 0 with that potential, and what happens in general at very high k, to see if there is a non-trivial minimum, or that we better find a non-trivial minimum at our phase, otherwise there is no space-time. And in fact, you see that here, because we have this change of sign here, there is for sure a non-trivial minimum if things do not run. So at least this is a good candidate to, at least as a toy model. So we should only use as a toy model. The question is whether we have a phase of unbroken diffeomorphism invariance, so that at very large k, this has a different shape. And then the other question would be, what if there is so, what is the nature of this phase transition? Is it first order, second order? But this is another kind of question we will be discussing later on. So how to look into the evolution, quantum evolution of this system, we had to use non-perturbative techniques. You cannot just do perturbative method here because gravity has this nice problem that is not renormalizable in perturbation theory. So we use Wilsonian renormalization group. And the equation I use is this one, which is a proper time functional renormalization group equation. You see the structure, you have a trace on a momentum space, and then you have a Schwinger proper time representation of this the second functional derivatives of your running action. This X actually is the gamma that was before in the discussion. Okay, and then you have a regulator here. You have this quantity is a regulator, and we use in this computation this type of regulators, which basically, I mean, they look a bit ugly, but if you take the derivative with respect time on this regulator, oops, I'm get confused here. They make sure that this, you see, usually you will have the divergence, UV divergence here at s equals 0. Now you can go up to s equals 0, and the UV basically behavior is regulated by these two functions. And of course, what we would like to have is something which at the end, at least for critical properties, should not depend too much on the shape of the regulator. Very good. So here, these two factors here, this Z, italic Z, has to be, there is some freedom, and you have to proper choose the Z in order to cut off the mode of the Laplacian at the right momentum. I mean, this is something a little bit technical, but it's not really important, so don't get hung in details. Yes, of course. No, the moment is not discrete. At the moment, I have not specified anything. Here, at the moment, there is no sphere, there is nothing. Everything is totally general. There is, at the moment, up to now, we have not chosen anything. In the next steps, I will make a choice. Up to now, there is no choice, and I have not. This equation here is fully, totally general. There is no approximation, nothing, whatever. And this trace is just a trace on the space-time that you would like to use at the moment. There is no approximation up to that. So the question, the conceptual question, which is extremely important now in this discussion, is that this trace, okay, the trace inside the flow equation must be performed on the modes of the background. That's really the background, how background independence is enforced in the background field method in quantum field theory, okay? If you miss this point, nothing will work. That is a crucial point. It's exactly what happens in the nonlinear case of the nonlinear sigma model. So you will have to regularize, to cut the modes here, because this is you have to use these. Those are the modes of box. Yes, those are the derivative with respect to the energy time of these two functions. We played different type of function, but the results is not very different. And n is the regulator. Actually, it's more convenient to go to the n equals infinity case, and one can show that in this limit, actually, this regulator is just a sharp cutoff in the proper time. So very simple. Then if you use this, you have to do the trace in momentum space. We also use a more complicated regulator where we also cut the modes of the box square things because we wanted to be sure that our result did not really depends on the regulator. But that's another technical details. I will not go into that too much. So let's see what happens, what do we have to compute. That's the flow equation that you have here. And that is the second function, the derivative of your action. And then you have the trace of this operator that you have to evaluate here. That is the regulator here, and that is the trace of the operator that you have to consider. And now we have to choose on which background we have to do that. And because we want to go up to identify in the right-hand side, in the left-hand side, we have all this term from gamma. In the left-hand side, you see you have all this term here. And so you have a term which is linear in R, another term which is proportional in lambda, another term which is quadratic in R hat. So what you do, you evaluate this trace here using the Gilkey heat kernel expansion on a maximally symmetric space up to second order. Because the only thing that you have to do is to write the beta function for your R and R squared term. Okay, so that doesn't really matter if you are in a sphere or not. The important thing is that you can get the beta function for this quantity here and this quantity here. So this, then you do this Seeley-Gilkey-DeWitt expansion for this operator. And in this case, you get, that is a usual term, and you get also the other term, which is quadratic in R. You do so, you solve the beta function. I will not show you the beta function because they are very, very long. But the nice thing is that there are fixed points. And this is the fixed point. This Z star is this quantity here. So let's look at the potential. So you have this Z here, okay? Then you have this beta here and lambda. These three quantities, they all flow to a fixed point. Oops, here. And this is basically there for any value of your cutoff regulator. So the fixed point is a real fixed point, it's not a fake fixed point. Okay, and you can look at your potential. What happens now, because you have the evolution to the potential near the fixed point. And it turns out that if phi, as it should be case like k, the potential goes to a constant. Therefore, at very close to this non-Gaussian fixed point, is non-Gaussian because this fixed point is 0, we must have a phase, at least in this toy model, of unbroken diffeomorphism invariance, so a pre-geometrical phase. And the nice thing is that the critical exponents here, you see, that's so nice to see that there is a very weak dependence on the critical exponents on the from the regulator, and the fixed points is attractive. That means that you basically have the following phase structure. That is the Newton constant, let's say dimensionless Newton constant, dimensionless lambda, and dimensionless beta, and they flow at very, very high energy. The very red part is the lambda goes to infinity. They flow to this non-Gaussian fixed point. So very good. Now the question is it really true, just an effect of R plus R squared? What happens in general case? Can we make progress on that? And the answer is yes. Imagine you have an action of this type. This is, of course, a very ugly action because it's not even covariant. You should suitably covariantize that. no, because that's not diffeomorphism invariant. But let's imagine there is another scalar field and you can make it covariant. And there are many people have been trying to generalize this to write a flow equation for this function of the determinant here times another function of G there. And this is a list of work that has been done in the recent year to solve this couple flow equation in a very, let's say, technical, complicated setting, because those people have been able to solve the flow equation in a fully gauge invariant way, which I did not do here. The problem is that if you try to do so, you get an infinite number of relevant directions. That means an infinite number of polynomials that you have to use to control the continuum limit. And the theory is no longer predictive. So that's not a very nice output that we like to have. So we repeat the same calculation in the following setting. Let's imagine we have this theory, as we know. We do the Weyl rescaling, so we end up to this theory. So there is not R square in this case. But to make life complicated enough, we imagine that we have a theory of this type. That's everybody knows this theory, just a scalar field, where Z is a function of phi and V is a function of phi, okay? And we would like to write the flow equation for this theory using the background independence. That means that if you have this type of term here, you have to use the P bar as a momentum. You have to cut the modes with the box bar operator, not with the box hat operator. That's the key point of background dependence, okay? So you can do that. So keep the traces perform on these modes, and you end up, that's rather complicate things, because this operator is not diagonal. Now, if Z is a function of a general function of phi and V is general function of phi, it will not be diagonal in the momentum space. So you have to use the Becker-Campbell-Hausdorff expansion of that operator. And this B1, B2, B3, I will not put in text because it's a very, very long expression, but everything is doable. And now you can imagine that your quantum field has a dynamical scaling. The conformal field usually is dimensionless. But at the quantum level, the conformal field may have an anomalous dimension. We would like to understand this anomalous dimension, because this anomalous dimension will be the key to the continuum limit. So how to get the anomalous dimension? Exactly as you do in the Ising model in quantum mechanics. You look for fixed point and you try to see whether there is a way of fixing the anomalous dimension. So the point is the following, that now if this B, you see, must scale anomalously, because usually in the classical theory, this eta is 0, and chi B and psi are dimensionless, your operator, your box operator, become anomalous. The Laplacian will not scale anymore as chi square, but it will scale with this anomalous dimension. So we are entering directly a structure which can only be described as a fractal spacetime. If you imagine you would like to discuss a diffusion process in a spacetime whose Laplacian does not scale as square of momentum, we are basically discussing a spacetime with a non-zero Hausdorff dimension. So you end up, after a long calculation, with these two flow equations. That is a general flow equation for the potential, and that is another flow equation for the wave function and normalization function. And when we saw these two equations, I said with Maria, there's no hope we can even imagine to solve this coupled set equation. But in principle, if we solve this equation, we will be able to see what happens at gravity at very high energies in this conformally reduced theory and determine the scaling dimension of the field. And now, because you have to trust yourself sometimes, so what you do, as you do in statistical mechanics, you go to dimensionless quantity, you rescale everything, and at the end, you get this nice coupled set of equations for the dimensionless quantities, which for the n equal infinity limit, they becomes much simpler. Look how nice is this equation for the dimensionless potential, and that is the equation for the dimensionless wave function or normalization function. The physical meaning of that, if I find a fixed point for this equation, that means that there is a non-Gaussian fixed point for gravity, and gravity is non-perturbative, renormalizable at this non-Gaussian fixed point. We would like to study fixed point solution. No, that's not conformal. That is the conformal factor of gravity, but gravity is not conformal. I'm not imposing that there is a conformal group. I am only quantizing phi for conformal quantum gravity. Okay, yes, but I'm just saying that there is no conformal group. But this is very general because this is a general function of x. X is the conformal factor. This z is a general function of x and whatever. If I find a solution of this equation, consistent solution of this equation with the non-zero eta, I basically get a dynamical determination of the anomalous dimension for the metric, which will not scale as as we know. We scale in a totally different way, depending on the value of eta. If eta is 0, everything will look classical. And some magic, because sometimes you have to be, some luck in life always helps. The magic is the following, that these two functions basically solve this, reduce actually the system that you have seen in these two algebraic equations. So what we do, we first look for fixed points. So we kill this term, and we have these two, let's say, terrible second order nonlinear equation. Well, it turns out that if you define this quantity and this other quantity, you get these two coupled equations for these. Those are just numbers, u and w, just two numbers. And so you have these two coupled differential algebraic transcendental equation as a function of the anomalous dimension. You can solve it depending on eta. And here is the magic. Okay, this is the Newton constant, dimensionless Newton constant. Okay, and this is the cosmological constant. Okay, U is a cosmological constant, and W is the Newton constant. And here is the value of eta. So now we can start doing physics. We would like to have Newton constant positive. So we better exclude this part. So eta, this part is rather unphysical. Also, this other part is rather unphysical because W will be negative. But all this branch is physical. Those are all fixed point, non-Gaussian fixed point for gravity, depending on eta. Are we done? No, because we have to study the stability. We have to study whether the theory is attractive or repulsive at this line of fixed point. So here is the nice thing. So from 1 to -5, we have this line of fixed point, and we would like to say whether we have a finite number of relevant direction and whether these relevant directions are basically eigendirection are attractive. Otherwise, the theory is repulsive. You just draw a line between 2 points and say, okay, I'm sorry, nothing works. So stability. You remember your beautiful equation here? Here, just let's study the second order equation. You study the stability around this line of fixed point. What you do, you write y as y star plus delta, zeta as zeta star plus delta, and we consider, but we can prove that those are basically the only one, this type of functions for the x part, for the radial, for the field dependent part, and try to get theta. If theta is positive, well, we are in business because the theory is normalizable. And linearized equations are this mess. And but also in this case, we can get explicit value for theta. And if we do so, here is the result. Here is eta. You remember before was eta. Physical, I mean, renormalizable theories, imaginary theta and real theta must be positive. So this is the set of all possible eigendirections which are physical. So here in principle, you will have an infinite amount of relevant direction, x6, x10, whatever. There is a pile, an infinite number of relevant directions, but they belong to this line that we saw before was predicting a negative cosmological Newton constant. So the only possible solution is here. So this is basically the cosmological constant, non-zero cosmological constant. This is that goes like in the conformal theory, like phi to the 4, and this is just the term in front of the kinetic term. And so we have only two relevant directions, and a line of fixed point. So very good. So the theory is predictive. It looks predictive. The other thing was also not very good because if the other value of beta, the Newton constant was not working. So what can we say about the ultraviolet critical manifold of this theory? That for eta greater than -5 and less than eta critical 0.96, this blue strip, the only relevant operator is the couple, this couple S of Rx quad. All higher powers are irrelevant, so they will not change the structure of the renormalized flow. For this value, the critical exponents are both reals, and for this value of beta, we have infinitely many relevant operators, and the theory is not predictive. So in this case, the theory is predictive despite the existence of a continuous line of fixed point. And now we can say the following: that does exist a phase of unbroken diffeomorphism invariance for which, oh, here is not equal, sorry, it must be not the phase is really equal to 0. Sorry for the mistake, because here the potential, this potential is just this, no? It's just phi to the 4 potential times the cosmological constant, which has a trivial minimum at x equals 0. So the bottom line of discussion is that at very, very high energy, let's say trans-Planckian energy, the conformal gravity predicts a phase of unbroken diffeomorphism invariance. You can talk about that as a pre-geometric phase or whatever. Then there is a scale of energy where geometry appears. You can think of that as a minimal length or something like that, which happens to be near the Planck scale, and then that should be used as initial condition for the Wheeler-DeWitt equation, because at that point we can exactly say what could be in this mini superspace approximation the effective geometry that, in my opinion, one should use as a boundary condition for the Wheeler-DeWitt equation, because the theory is now ultraviolet finite. In principle, I can go to arbitrary high energies and everything is finite. So last comment about gauge invariance. we had to pay a big price. We had to choose a background. Okay, our things is not background independent. So what is the meaning of that? So usually in textbook, there is always a discussion. Should they, if we talk about coordinate transformation, should we interpret in active or passive transformation? And usually, in general relativity, mathematician talks about diffeomorphism as active transformation, coordinate transformation, passive point transformation. And there is no clear way at the classical level to interpret this as active or passive. Nobody can come up with a difference in physical prediction. At the quantum level, things are different. And for physicists, usually gauge transformation are passive alterations, and mathematicians instead tend to view gauge transformation as active changes. So mathematician thinks, really, I take a point, I move a point in this other place in the manifold, these things like that. It's really a cultural question now. And the point is that this is okay when we work only with dynamical physics, but when we introduce background field into the game, we are breaking this equivalence, of course. This equivalence is not there anyway. So I think it's we should divide at some point weak gauge invariance and strong gauge invariance, and divide these two in weak gauge invariance vary in the passive transformation, and strong is invariance and the passive and active transformation. I think that measurable quantities, like quantities that can be extracted from experimental data, must be gauge invariant, but of course weak or strong. If we think to QCD, gauge fields are gauge fields. They do not exist as asymptotic states. But do we say they are unphysical? No, because we see that Parton distribution changes, and we can measure the fact that there is an physical effect in the Parton distribution. So even in the presence of a field for which there are no asymptotic states, you can define observables. And in the case of the background field, I think that this is something that we should keep in mind. So okay, that's my, let's say, philosophical discussion about gauge invariance in quantum gravity, which I'm sure people from the loop quantum gravity community will not agree on that. But anyway, that's what I'm at the moment thinking about. The conclusion are the following: that conformally reduced R plus R squared theory lies in the same universality class of the full theory. So if we have not done this conformal reduction, the work of Reuter and Loescher in the early 2000s, where they included all the degrees of freedom, basically shows the same results that I've shown you, which means that the conformal factor is the key to the non-Gaussian fixed point. The other degrees of freedom, they do not really make the non-Gaussian fixed point. They only move the fixed point in this parameter space. The structure of the ultraviolet critical manifold is finite, has a finite dimensionality in a controlled background field expansion, as I've seen. And the physics of near the non-Gaussian fixed point is characterized by a pre-geometrical phase for which we do not have even geometry. There is no geometry. At least no, imagine that you have a statistical case where you have change of topology and whatever it is, but the mean value is 0. Then you go down in energy, and eventually this will be different from 0 around the Planck scale. And I think that this approach is a promising approach to define the initial condition for the wave function of the universe and the Wheeler-DeWitt equation. Thank you very much for your attention.
Questions?
Thank you for the lecture. You say your theory is UV complete, but at some point you show the differential equation and you said you can't solve that equation,
No,
right?
I solved that. That is the solution of the differential equation.
Yeah, but you solved for that choice of that choice of y, and
That's the only that is a second order solution. We know the solution is unique.
so that two lines there are not derivatives, those lines.
This are derivatives, and this is an analytic solution, and because of Cauchy-Kovalevsky theorem, it's the solution that satisfies the boundary condition is unique. That is the unique solution of those. Unless you violate the initial data, you violate. This is really a second order differential equation for which we know we have theorem of exact theorems about unicity of the solution.
Okay, thank you.
That's why I said it's a miracle that you can do that. That not always happens.
In the case of effective field theory, some of the dimensions seems to be special. Some of your expressions blow up when any d equal to 1 and d equal to 2, right?
This has nothing to do with effective field theory. Effective field theory is an expansion in the inverse of the mass Planck, inverse mass Planck expansion. There is no inverse mass Planck expansion here because we are fully non-perturbative. So there's no way you can compare this with any calculation in the effective field theory community.
I'm talking about some of the expressions. You can go back, maybe equation 17 or something before that. You have some d minus 2s in the denominator, so d equal to 2, they automatically blow up much before.
No.
Before.
Where is it?
When you write down the potentials for the effective field theory, much before, yes.
Yeah, but this is...
Here is one. And before that you have in the...
No, but this is nothing to do with effective field theory. Wait, in d equal 2, you have no field equations.
That's correct, right?
So, but that's nothing to do with the field effective field theory.
That's correct. Go back. Mm-hmm.
Here, what do you have? No, before.
Still, yes.
Sorry.
Okay, still go back. What about, yeah, here, look. Yeah, here, and even before, there are some special places where some dimensions are not allowed, right? So here, even before, you can go 1 or 2 slides before and you have it.
No, you can keep any dimension greater than 2 is allowed. There is no problem with dimensions as long as d
is greater than 2, right? Yes.
There must be so. D equal 2, it makes no sense.
Go back one before, right? So there may be. Okay, it's all right.
More questions? Okay, let's thank Professor.
Thank you, man.